Welcome to the tutorial, and welcome to Colorado, and welcome to Vail. And I'm actually really excited to finally address members of the information theory community on aspects related to submodularity, because on the one hand, as probably some of you know, and as we will cover in this tutorial, submodularity has deep relationships with some of the concepts that exist in information theory. And in fact, some of my own learnings and some of my own readings, in fact, quite a bit of my readings on submodularity has come from papers in the IT community. But on the other hand, there are some very distinct and new and interesting phenomena associated with submodularity that actually have been developed in the machine learning and the data science and, if you want to call it that, the artificial intelligence communities that perhaps have led us into directions that wouldn't have happened had it been purely in the information theory community. So one of the purposes of this tutorial is to try to hook some of that back to you guys so that you guys can then carry forward and continue in the IT world. So my background, I'm a professor at the University of Washington, Seattle, and I do primarily machine learning stuff. And I have a great interest in information theory and have had a great interest in it for many years, although I haven't really published in this community very much, or actually at all. Okay, so one thing about the tutorial, just to begin with, is that if you look at this definition of submodular functions, or even if you take the entire tutorial that we're about to give, it's really only the tip of the iceberg of a very, very deep mathematical property of certain classes of functions. And it's amazing how something so simple at the beginning can branch out into something so complex and so beautiful. And so I'm hoping that if we've succeeded in our tutorial, we've inspired some of you to go and read more about this material in the machine learning community, because there's a lot of interesting stuff coming out there on this topic, as well as in the discrete optimization community as well, which is, of course, historically where a lot of the material appeared. I also want to mention before we begin that there have been other tutorials on submodularity in the past, primarily in the machine learning community, and also, of course, with the machine learning slant. And there was a NIPS tutorial in 2003, a tutorial in 2013 ICML tutorial. Andreas Krauss, who's a good friend of both of ours, has a web page on it. And there's some interesting written material, very recent, or relatively recent, again, from the perspective of machine learning and optimization, convex optimization, as well as a 40-hour YouTube set of lectures on submodularity, which, if you're interested in visual or up-to-date recent material, you can go to read further. Okay, so here's an outline. As Amin said, there's two parts. There's part one, which is the foundations, and I'm Jeff Bilmes. I'm doing part one. And it's going to consist of, I guess, 5 parts: an introduction, some definitions, some examples and properties. We're going to talk about the goals of optimization without actually talking about optimization algorithms or guarantees. And lastly, talk about some applications. And then secondly, about after 1 hour and 20 minutes, we're going to go into part 2. First, we'll take a break so everybody can get some coffee or watch the World Cup, whatever you do. And then we're going to come back and talk about algorithms and their guarantees. Now, as you'll find out at the end of this tutorial, one of the things interesting about submodularity is not only are they natural for many real-world physical phenomena, but for the same property that makes them natural for modeling many real-world phenomena also allows them to have efficient algorithms. And that's what Amin's side of the tutorial will be about. Okay, still on the topic of outlines. So this is the outline of part 1, the first half. And why don't we just go right into it, because we're going to be visiting this outline multiple times. So let's start with background. Okay. And by the way, does anyone hear our next door tutorial better than mine? So these guys are very loud. It's a little bit distracting for me. So if I occasionally start talking about whatever they're talking about, just please bear with me, because I can hear them better than I can hear me. So if I sound distracted, you know why. Okay, so we're talking about primarily set functions. And what a set function is, it's a function that maps. We have some underlying ground set V. So V is some set of objects. Usually, like, the size of V is lowercase n. And we consider all possible subsets of V, which is the power set of V, which is typically what we use. And so here would be, for example, a set of objects. And these objects are images of certain types. like you have sushi objects and nature objects and insects and scientific instruments and squiggles and maybe some other things. And basically, any subset of the set of objects is such that you can value that set of objects. So like a given set, like if we take A, like here's a subset which consists just of the sushi items, a set function would then value that subset. So what this immediately means, sorry, here's another subset. So this is a subset that consists of the diversity of different objects that there are. There's a squiggle and a sushi and a tree and an insect and a cloud and a scientific instrument. And that's a different set that has a different valuation. So a set function is something that provides a value for every possible subset. So that means a set function in its most general form has 2 to the n possible valuations. So it's a set function is a vector in R to the 2 to the n dimensional space. A submodular function is a set function that has additional constraints associated with it. And it's actually got quite a bit of constraints. So a set function is submodular if it's the case that for any sets A and B, this inequality is true. So f of A plus f of B is greater than or equal to f of the union plus f of the intersection. And that's one of the classic definitions of submodularity that you see all throughout the literature. In fact, it goes back almost 100 years that you see this inequality showing up. It's kind of amazing that this appears. And then another mathematically identical definition of submodularity is something that you can perhaps call diminishing returns. Some people think of this as more intuitive. And that's basically an inequality that says that if you have 2 subsets, one which is a superset of the other, so B is bigger than A, and you have some element V which is not in B, when you look at how much the gain is of V adding to the set A, so when you look at the left-hand side here, this is how much does V improve upon A. And so that's basically greater than how much V improves upon B. So that's diminishing returns. In other words, basically it says that the more you have, as you go from A to B, you're getting more stuff. The less, if you think about this as a value function, the more you have, the less valuable anything you don't have becomes. V becomes less valuable as you get more stuff. And that's diminishing returns. So I want to also talk about the definition of a supermodular function. So the difference between a submodular function, we're saying that it's diminishing returns here, and f of A plus f of B is greater than or equal to this. A supermodular function has switched the direction of the inequality. And also here it switches the direction of the inequality, and it's called increasing returns. So there it's basically saying that the more you have, the more valuable what you don't have becomes. Submodularity is the more you have, the less valuable what you don't have becomes. Supermodularity is the more you have, the more valuable anything you don't have becomes. Now at the bottom of this slide, there's a couple of other definitions. So we can, first of all, immediately see that a function is submodular if and only if its negation is supermodular, and of course vice versa. And if a function is both submodular and supermodular, and it's said to be modular. And any modular function can be written in this way based on a sum of its, essentially its singleton values. So a modular function consists of, if the size of the set V is n, then a modular function is no longer 2 to the n possible values. It's only n plus 1 possible values. And most of the time, in most data science applications, we assume that C is equal to 0, in which case the function is said to be normalized. So a normalized modular function is one that, is that Hamad? Hey, how's it going? So a normalized modular function is one that, I'm surprised you're not watching the World Cup. So a normalized modular function is one for which you only have n possible values, or you can think of any set function being normalized if its value on the empty set is equal to 0. Okay. All right, so just a little bit more notation. So on the modular functions, this tutorial is not going to be all definitions and notation, but I just want to get through a couple of things first so we can refer back to them later. A normalized modular function is often, like as I just said, you can think of it as a vector in V-dimensional space, where V is the original set, and you can think of the elements of V as naming the dimensionality of the vector. So R to the V really is R to the N. And each dimension has a name which corresponds to one of the elements in the set. And then you can also evaluate a modular function. So any set A evaluated according to the modular function is just basically the sum of the individual entities. And so many problems, like many discrete problems, end up using modular valuations. Like when you go to the store and you buy a bunch of items, like there's the cost of this item, and the cost of this item, and the cost of this item, and the cost of this item. And you add up all of those costs, and that's the total cost of your trip to the store. The items themselves don't affect each other's costs most of the time, but every once in a while you'll have like a 2-for-1 deal, where if you buy one item, then the second item, the price of the second item is influenced by the fact that you've purchased, that you've selected the first item. And that, in fact, ends up being a simple submodular function because the second item cost is diminished. It's a diminishing returns. In a modular function, there's no interaction of costs. You just add up all the costs blithely without thinking about the other items that you're considering. So modular functions are, in some sense, the simplest of the functions. Another thing that I want to also just define notationally is this idea of conditional gain. Oh, sure. Actually, thank you for doing that, because I forgot to say, if anyone has any questions, please ask them. So, yeah, so the question is, are these two things the same thing? I think I'm hearing what you're saying over what's happening next door. So yes, so what we're saying here is that m is a modular function, and m is equivalent to a vector, which is n values. It's a normalized modular function. And then it evaluates. So whenever we have a set A, so A is a subset of V, whenever we have a set A, the evaluation of the modular function just sums up the singleton valuations. Yeah, so this is this thing here. So this is just how you get a value from this modular function. So if A is a set. This m here? Is this true? Is what true? The second m, which is a vector. This m, yeah. Yes, it is as the sum n in the sum. Yes, so what we're saying is that a modular function is equivalent to a vector, and then when you want to evaluate it on a set, you just sum up the corresponding dimensions associated with the set A. Okay? A is a subset of V, and remember the dimensions are named by the elements of the set V. And so what we're doing is summing up the elements associated with the subset A, which is a subset of the elements of V. Okay? Is that the A, which is a singleton, then you omit the bracket? That's omit. Yeah. So if you're worried about the notation now, there's a lot more notation you're going to be much more worried about later. So I would hold on your concern. I think we should wait till after the talk, because like I said, I think if this is unclear, then nothing else will make sense. So, okay, so let's go forward. So the other thing is the conditional gain. So the conditional gain of a set function is defined this way. So you're given two sets, A and B. And what the conditional gain is defined, this is something that comes up all the time, and so we're going to be using it relatively freely. And so I'm hoping that people understand this, that this is f of A given B is basically is f of the union plus f of the second one. So f of A union B plus f of B. And so we're using this notation, and it should be somewhat familiar to people who are familiar with the notion of conditional entropy. Okay, so the other thing that one should note is, of course, since everything is a set, f of A given B is equal to the same of f of A except for B given B, right? Because when we take the union of A and B, that's the same as taking the union of A except for B union B. Right, so that's the same valuation. And then oftentimes when we look at the gain, the set A consists of just a single value, which is just 1. It's one element, and so its size is 1. And so whenever we take an A that's not in the set B, we can write f of the element A given B as f of B plus A minus f of B. Okay? All right, any further questions about this notation, besides the one you just asked? Okay. So like I said before, I'm kind of happy to give this talk in front of an IT-friendly audience because I can finally quote Shannon. I mean, who would go to an information theory conference without quoting Shannon, right? So one of the things that's interesting about Shannon's classic 1948 paper was not only that he defined the entropy function, but he also showed that the entropy function is subadditive in a way that we're going to talk about in a minute. One of the things that we're going to be looking at that's slightly different than the way probably some people are familiar with looking at the entropy function is that we're looking at the entropy function, f of A, where A is the index set of a set of random variables. So like h of x of sub A, so this is a vector. x of A is a vector where the elements are chosen corresponding to the set A, and it corresponds to this. So basically, this is a sum over the alphabet of x of A, and of course, it's this summation, how long it takes to compute that. If you were to compute that naively and exactly, it would be exponential in the size of the set A, right? Okay, so that's how we're going to be viewing the entropy function, as a function of the indices of the set of random variables. And there's some underlying random distribution, P of xa, this being P of xv, this being the marginal distribution over the random variables associated with set A. Okay? Okay, so interestingly, so as I said, so Shannon showed that the entropy function is subadditive. So these are actually quotes directly from, in fact, they're screen captures directly from his 1948 paper. And so he argued for entropy being natural as an information function for the following reasons. So first of all, he said the quantity h, the entropy, has a number of interesting properties which further substantiate it as a reasonable measure of choice or information. Okay, and then later on, page 395, he said it's easily shown that h of xy is associated with the h of x plus h of y. So basically, this is the subadditivity property. Any function, so you could think of this as one random variable, this is another random variable, and when we take the union of this, you can think of this as the union of two sets, right? One set having a size 1, another set having a size of 1. We take the union of two sets, we have a set of size 2, it's h of xy. That's a subadditivity property. And then on page 396, basically said the following, right? And hence, deducing the following equation that h of y is greater than or equal to h of y given z, right? So in other words, that means that conditioning reduces entropy. Right? Now, that conditioning reduces entropy, basically is the same as what we would call subadditivity of a set function. Here's what we would call subadditivity more generally, that basically if we have sets A and B, that f of A union B is less than or equal to f of A plus f of B. Now, the question was, or this question is that we were interested in asking is, did Shannon prove, therefore, that entropy is submodular back in 1948? It turns out that, at least when you look through his paper, there's nowhere that he actually stated something that is identical to the submodularity of entropy. And here's an example showing that if you have a monotone and subadditive function, namely equation 9, then that doesn't necessarily imply that the function is also submodular. So like here's a monotone. You can see clearly that this function is monotone. And the reason why it's subadditive is because of the second term. Because if you union these two things together, chances are that eventually A in the bigger set is going to become greater than K, and you're not going to get that additional increment. Whereas you do have the more possibility of getting the increment for the things that you're unioning together. So this function is subadditive, and it's also monotone. But here's an example. If we set K, a very simple example, if you set K is equal to 1 and A and B both to size 2 sets, and it's an example of where the function is not submodular. Okay, so the question is, when was entropy known to be submodular? So if you go back to 1954, to McGill's paper, Multivariate Information Transmission, he started, for the first time, at least as far as I could see, talking about entropy over more than just 2 random variables, and had 3 random variables, in this case, u, y, and v, and came to the conclusion and that this was true. Basically, this is using this notation back in the early 50s, that h of y given u is greater than h of y given u and v, which using modern notation looks like this. So this is the same as this. And he actually attributed it to Shannon, but then when you look at Shannon, Shannon actually never said this. But if you expand this inequality, this is exactly the same as this. And this equation 11 is exactly the submodular inequality. Now, interestingly enough, oftentimes people will say that this is the first paper in 1978 that was the first to show the polymatroidality, the submodularity of the entropy function. But I think maybe it goes back to McGill. So fine. So then we've got the Shannon inequality properties turn out to be identical to what people in the submodularity community would call polymatroidality. Namely, we've got a non-negative set function so that all valuations are non-negative. It's monotone, so if we take any B, which is a superset of A, the valuation of B can't be any less than the valuation of A. and submodularity. So if we have these three properties, non-negative, monotone, non-decreasing, submodular, that's a polymatroid function. And those are what in the IT community is sometimes called the Shannon inequalities. Okay, so now this is where we're still in the IT community. So Zhang and Jung, and I think Jung is actually giving a tutorial is he next door? Or he's giving a tutorial here. Maybe you should go see his tutorial and not listen to me. But anyway, his paper in 1998 actually found there was this question in the IT community about whether or not the polymatroidal inequalities were sufficient to characterize all entropy functions. And what these guys found in 98 was that the entropy function satisfies additional inequality. He's right there. Oh, you're right there. Okay, so you did this. So maybe you should listen to him. Right. So these guys found that there's an additional inequality that entropy functions must satisfy that is not derivable just from starting from the polymatroidal inequalities. Right. So that's interesting. Right. Now, this is where we now diverge from the IT community and the maybe data science community, if you will. So from an IT perspective, this is kind of interesting because it narrows the scope of the entropy function. It says, okay, cool, there's other inequalities we can use in the entropy function. We can prove theorems about entropy that we couldn't prove before. We know more about the entropy function. And there are a number of papers, some of which involved computer-generated searching of inequalities of the entropy function. In fact, found there's quite a few of them. There's, I think, an exponential number of additional inequalities associated with the entropy function, not derivable from the polymatroidal inequality. That's one branch. The other branch from the data science community is the following. This is the one that we take. It says, well, wait a second. Shannon and maybe McGill argued that the Shannon inequalities, the polymatroidality inequalities, were sufficient to characterize a natural information function. So why should we then necessarily stay with entropy? I mean, entropy is, of course, great for a lot of things, but maybe there are other uses of information functions that don't involve probability distributions and that are easier to manage, but that still satisfy the Shannon inequalities or the polymatroidality inequalities that we can use for science applications. And maybe, in fact, there are other algorithms associated with it. And that's exactly these questions that hopefully the rest of this tutorial will answer in the affirmative, which is number one, there are other information, quote, information functions. They're not information functions in the Shannon sense, but they are, characterizable as information functions. And number two, the other question is, are these other properties, like the submodularity property, sufficient to allow for scalable, low-order polynomial time algorithms that optimize over these combinatorial spaces with mathematical guarantees? And this is where Amin's part of the tutorial will kick in. So both of these things are true, interestingly enough. Okay, so question is, what is information? So obviously, we do have information theory. We have the entropy function. Everyone here, I believe, knows a lot about the information function, or sorry, the entropy function and why it's a useful information function. Also from the IT community, there's Kolmogorov complexity, which is like a form of algorithmic complexity. It basically says that the information in a source corresponds to the shortest program description that generates that source, right? From a practical perspective, like let's say you want to measure, you want to say, here's a large collection of images, and there's a certain amount of information, and we're working with units of subsets of images. How do we find a subset of images to do, say, for example, like a summarization process? How do we find a subset of images that preserves the information in all of the images? You could think of perhaps compressing them and using like the entropy, or you could Kolmogorov complexity is completely impractical. That's not really something you can actually do to solve problems. But it turns out that submodularity allows for a lot of other, quote, information functions, all of which satisfy the submodular inequality, and that are practical and useful. Okay, so what are then the desirable properties? This is another way of motivating submodularity. What are some of the desirable properties of an information function? So let's say that V is a finite set, and then say that A is a subset of B, which is a subset of V, and lowercase v is some element not in B. And let's say that we want f to be an information function. So what might we want for f? Maybe we'd want non-negativity. I think it's arguable, like we could kind of take that or leave it. But let's say that, maybe if you want it, you can have it or not. Perhaps you'd also want monotonicity. Like the more you've got, the more you know, perhaps. And so maybe that should be monotonic. Although there's some people who believe that, the more you know, maybe it raises questions and maybe it creates more lack of knowledge because now at least you know what you don't know. I don't know why this is sort of automatically going, so I'm going to unplug this thing. The slides are advancing without me touching anything. So let's, perhaps also we want subadditivity, where, what subadditivity is, again, the property of the entropy function that Shannon proved, which is that, you could think of this as f of a plus v minus f of a is less than or equal to f of v, right? So that data, namely a, can only inform you about other data. So like a is something that can only inform you about v. But let's define this other thing called a knowledge of function. So the knowledge of function is meant to be, and it's meant to convey the knowledge that the data in set A has about element v. And let's define it in the following way. So it's 1 minus f of a plus v minus f of a divided by f of v. And this is a number between 0 and 1. And the idea is that if f of a given v is equal to 1, that means that a has complete knowledge about v. The set A tells you everything about v. And if the knowledge of v given a is equal to 0, then basically it says that the set A has no knowledge about v. It's complete lack of knowledge about v. So if it's the case that we say that more data should tell you no less, namely, if we say that for all subsets A of B, that the knowledge of v by A is less than the knowledge of v by B, in other words, more tells you more, then it turns out that that property, equation 14, is identical to the definition of submodular, irrespective of whether or not you assume non-negativity or monotonicity. So this property, knowledge, like the more you get, the more you know about something that you don't know, is exactly the definition of submodularity. And so if that is sufficient to sort of characterize, at least intuitively, what we would want to be true about an information function, then it also means that any submodular function can be seen as an information function. But if it's negative?
Yeah, you said that it's not necessary, that submodular changes.
Yeah, I mean, I think it's, let me put it this way. So this alone, without assuming these, requires define submodularity. It doesn't necessarily mean that this is between 0 and 1, okay? But it does guarantee that it's submodular. So like maybe you'd want this to be between 0 and 1, in which case you'd want these guys too. But if you really want to say that the knowledge of, and if you're willing to have negative knowledge of things, I mean, the main point is that you have this increase in knowledge. So if it's negative, it becomes less negative. If it's positive, it becomes more positive. Okay. So therefore, I mean, this should also be familiar with people who are familiar with IT concepts. We can, given any submodular function, define notions of dependence, what to call combinatorial independence or combinatorial dependence, combinatorial mutual information, combinatorial mutual information amongst subsets of a set in the following way. So, deep independence would mean that f of a union b is equal to f of a plus f of b. For any submodular function, it's combinatorial independence. Conditional independence would mean this. Dependence would mean this. And then conditional mutual information, combinatorial conditional mutual information would mean this. And then information amongst sets would be this. Now this is, again, all I'm doing is just plugging in submodular functions where ordinarily in the IT community you'd have the entropy function. But now we get something that is equally interpretable, but for things that don't require entropy probability distributions or the cost of querying the entropy function. One of the things I did mention, of course, is, and I'll mention it again, is that if you want to use the entropy function for actually measuring information on data, you actually need, to, if you're doing it non-approximately and naively, you need to spend an exponential amount of time just for one entropy query. And you need to get the probability distribution, which is itself a difficult problem in high-dimensional spaces. Now, there are many ways of defining submodular functions. And this is just sort of a characterization. Every one of these, this is the standard one that we saw, 19. This is another one. This is diminishing returns. This is a form of conditional subadditivity. This is something called 4 points. This is another strange form of conditional subadditivity. And then these are other ways of defining. Each one of them is equivalent, including this one at the bottom, which basically says if you take a polyhedron and you take any maximal vector contained in the polyhedron that's a subvector of some other vector, if it has the same component sum, there's even a sort of a geometric way of defining submodularity, this polyhedral description. So any one of them is a definition of submodularity. And where these came from is from all over the place. I mean, there are lots of communities that actually rediscovered submodularity for different purposes, including the IT community. I mean, if you think about it, McGill's discovery in 1954 was, in some sense, a discovery of the submodularity property, although it was known much before then, although back then there wasn't Google, so it wasn't possible to discover this. And interestingly enough, there's an equally wide-ranging number of names that refer to submodular functions. Of course, there's submodular functions, attractive, associative, regular, ferromagnetic, pot, subadditive, strong subadditive, quasi-antitone, two-antitone, and so on and so forth, including Monge, Fisher-Hadamard, Kota, Jensky, multivariate totally positive of order 2. These are all names that in the literature people have used to refer to functions which are submodular. So from the perspective of coevolution and mathematical coevolution, this basically probably means that there's something really fundamental going on about submodularity if it's the case that it's independently rediscovered all over the place repeatedly. Okay, so what are some useful submodular functions that we use in data science? One of the things that, like, in fact, this is sort of a little bit of a personal story for me because I became interested in information theory because I wanted to actually measure information in actual data sets. And then I worked with my students on some ways of trying to estimate the entropy from data. And it's expensive, it's costly, and it's only approximate, and you have to worry about bias variance trade-offs. Then when submodularity I became aware of that, I said, wait a second, we don't need to use the entropy function. There are other ways of measuring information in data. But what are some of the ways you can do so that are computationally advantageous? Well, before we do that, actually, I think I'm going to skip this. Actually, let me give this one example, and then I'm going to skip the next example, just to give you sort of an idea of submodular relationships in real-world objects without there being essentially a probability distribution associated with it. So let's say that you have 3 objects, or possibly 3 objects. So you have some subset of these 3 objects, so you have 8 possibilities, from the empty set to all 3. And you have a value to yourself of how much you're willing to pay for any subset of these 3 objects. The 3 objects are a cup of coffee, a cup of tea, and some lemon. Okay, so you have a value for each one of these objects individually, like you'd be willing to pay $5.50 for a cappuccino, right, or something, and similarly for a cup of tea and for some lemon. But now once you've got a cup of coffee, your value for a cup of tea is diminished, right, because you've already got coffee, you don't need tea. And similarly, once you've got a cup of tea, your value for a cup of coffee is diminished. You don't need coffee once you've got a cup of tea. So therefore, coffee and tea are what you could think of as substitutive, or in fact, this is a submodular function on 2 items. Once you've got one, the value diminishes of the other. Now let's consider coffee and lemon. Like if you've got a cup of coffee, maybe the value for a lemon wouldn't be influenced by the case of you having a cup of coffee or not. So the value of lemon is kind of independent. It's like it doesn't matter. It doesn't change whether or not you have got a cup of coffee. You're willing to pay the same price. Whereas once you've got a cup of tea, suddenly your value for lemon would probably increase because if you've got a tea and lemon go well together, they're complementary. And so therefore, their price, tea and lemon together, you would value greater than the sum of their individual prices. Unlike coffee and tea, the price of coffee and tea together, their value priced together would be less than the sum of their individual prices. So coffee and tea are in a submodular relationship with respect to each other. Tea and lemon are in a supermodular relationship with respect to each other. And it only has to do with your own value of these objects. It has nothing to do with there being a distribution. These are just presence or absence of objects. And so a lot of the things that we do, so there's a lot of work in the machine learning community for example, once you've got a submodular function, how do you optimize it? How do you control it? And Amin's part of the tutorial is going to talk a lot about that. But a lot of other things that we do in the machine learning community is how do you produce a submodular function over data items like images or like videos or like various forms of like database records or any collection of data items that are you can think of as being a set of data items and possibly choosing subsets of data items. I'm going to skip this example. for time reasons. Okay, so a classic submodular function is the number of colors of balls in an urn. So I always say that there's no good concept in computer science that can't be explained by balls and urns, and submodularity is no exception to this. And so basically here, the value of the urn is not the number of balls in the urn, but is instead the number of distinct colors in the urn. So on the left-hand side, you've got 2 colors. The value is 2. You add in a blue ball, you increase the value by 1 to 3. On the right-hand side, you've got already a couple of blue balls in there. You add in a third blue ball. The value was 3 before you added the third blue ball, and it stays 3 once you've added the third blue ball. This is a classic submodular function. And in general, submodularity is very good for measuring diversity of types. So in this particular case, it measures the diversity of distinct colors in ball. When you have a set whose value is large with respect to a submodular function, oftentimes we say that it's highly diverse. Submodular functions are great models of diversity. In order to try to come up with a ball example for supermodular functions, let's consider the following ball pyramids. So we've got a size, and in this case, we've got V is equal to 10 balls on the bottom. So this is our ground set. And we choose a subset of balls, and we draw lines at 45-degree and 135-degree angles from that ball. And then any ball in the pyramid that is intersected by 2 lines gets counted in the valuation of the subset that's chosen of the balls on the bottom row. So here's an example where the number of balls is 10. We've chosen ball 2, 5, and 9. We've drawn these lines. There's only 3 balls that have 2 lines, and so therefore the value of these 3 balls down here in the set A is equal to 3. Over here, we've added a 4th ball. We've added ball number 4. And so what happens is that the valuation has gone from 3 to 6. But now here's a larger context. B is 2, 4, 4, 8, and 9. Notice that this is a subset. B is a superset of A. So this is 2, 5, 9, and this is 2, 5, 9, 8. And then when we add 4 to this larger context, the increase, 10 minus 6, which is 4, is greater than 6 minus 3, which is 3. Hence, this is a hand-wavy proof of the supermodularity of the ball pyramid. Okay. So does everybody get that idea? Kind of, sort of? Okay, that's the simplest example of a supermodular function I could think of that uses balls. So, but here's some real example functions. It turns out that there's a whole swath of different submodular functions that we could use and that are practical and useful. And they include a lot of things like set cover and vertex cover, and a lot of graph functions, edge cover, graph cut functions, bipartite neighborhood functions, facility locations, sums of weighted concave functions composed with additive functions, various matroid ranks like the log determinant is a submodular function. Of course, entropy, a lot of the information theory functions are submodular. Various forms of spectral functions applied to Hermitian matrices. There's a large class of functions, many of which are simpler than entropy. Of course, the log determinant function is a classic submodular function. It's the same as the Gaussian entropy. That's a trivial way of proving the submodularity of that function. But one of the things I want to do is to show you some of the functions that we've used that have been particularly useful in data science, starting with the facility location function. Facility location function actually goes back to the 1960s, where people's primary concern was how to pack boxes in trucks better. And the people who were thinking about how to pack boxes in trucks better came up also with ideas on how do you decide where to place factories near cities in such a way that each city is well served by a factory, by a supply, I guess it's associated with supply chain management, and you want to make sure that the cities have sufficient supply of all of their needs. And so the idea is that you could think of V as a set of cities, and A is a subset of V. A is a subset of locations where you might want to put a factory. And then this is S could be thought of as say like the similarity, or like how it becomes larger the closer the factory is to the city. And so you evaluate set A by considering all possible cities, and you find the closest or the most similar hypothesized location of a factory to this city V, and then you sum all of the possible things together. So this is a classic submodular function, the facility location function. And more generally, this can actually be used for data science. If you're trying to define a facility location function over data sets, all you really need is a similarity measure. The only requirement is that S be non-negative. And that basically says that any subset A, the degree to which A is a good representative of the whole, corresponds to, for every single item in the data set you're interested in representing, how close is the closest item in A to each one of those items in the set that you're trying to represent. That's the facility location function. Another commonly used function is what's called the weighted coverage function. So this is like a set cover function with weights. So here, basically, U is some set. So it's not the set V. It's a different set. And then for every set V in V, let's say that we've got U sub V, which is a subset of U, and we have a weight. This is a modular function defined on U. And it's a non-negative modular function defined on the elements of U. And then this function F is defined as taking the weights of the union of all of the sets associated with the argument A. Or another way of writing it is basically saying U is in the union of all of the U's, and then we're summing up the weights of U. So that's a classic submodular function. In fact, if we just take the weights to be 1, then it becomes a set cover function. And more generally, if the weights are any non-negative weights of all of the elements in U, it becomes a set cover function. So another interesting class of submodular functions. So one thing I want to make sure is clear here is that these are classes of functions. This is not any one function. It's a whole class. So consider the following class is basically saying that the valuation of A, it's called the sums of weighted cardinality truncations. And the valuation of A comes by summing over all subsets of B and then over all sizes between 1 and 1 less than the size of the current outer summation index. And you have some weight, which is non-negative, and you're taking the truncated version of this cardinality. So you're saying what's the intersection between A and this element B, and then truncating it at I, and then weighting that thing. So any such function is also submodular. Still other class of submodular functions is when you compose concave functions with non-negative modular functions. So if you have a non-negative modular function and a concave function, then the following function is submodular. So here's an example of a concave function. And the idea is kind of simple. It's saying, if you have a given increment going from m of A to m of A plus V, this increment, if you do it in a smaller context, A, this increment is going to be larger than if you add the element B, because this horizontal movement is the same here or here, but the gain you get is going to be diminished thanks to the concavity applied to the modular function. So if the concave function is a linear function, then of course this gain is going to be the same, and you're going to get back another modular function, because a linear function composed with a modular function is still going to give you a modular function. But then this gives you sort of a very intuitive idea of the notion of diminishing returns, right? Because it's saying the more you've got, the less valuable anything you don't have becomes. So then, if you take a non-negative weighted sum of these concave over modular functions, you get what's known as the class of sums of concave composed with non-negative modular functions plus modular functions. Here, there's no final modular function, but you can see that this has this form here. It's just a weighted sum of these guys. And then another class of functions, this is also a fairly recent class of functions, is called deep submodular functions. There's been a lot of interest, of course, in deep neural networks in the machine learning community that I'm sure everybody's aware of. It turns out that you can actually define a class of submodular functions in a way that's analogous to the way that deep neural networks are defined. And the way it works, there's a lot of notation here, but basically the way it works is that you start with a function like this, and then you put one concave function on top of that. You compose that whole thing with a concave function. In fact, you compose this with a lot of concave functions here, which is down in this way. So like this is an example of, this is a modular function, and this is the first concave composed with modular. And then you take a weighted sum of those concave functions, and then you compose it with another sum of weighted concave functions. And you just keep doing this recursive nested decomposition of concave composed with modular functions, each of which is concave composed with modular functions, down to the original input. And that defines this class of deep submodular functions. So it's very analogous to a deep neural network, right? Because you could say, okay, this this is the input. This is these are indicators of what set you have. You could think of these are binary indicators. And this is basically a concave composed with a modular function, which is essentially the sum of the elements corresponding to which input you have. And this would be another one and another one and another one. And then you're taking recursively defined compositions of more concave functions composed with these ones, and so on and so forth. So, the question is, why is this interesting? Well, it's interesting for a number of reasons. One, because you can prove that the families of the functions are truly different. This is something, to be honest, I was inspired by Raymond Young's paper from '98 to look at additional classes of submodular functions to try to understand, can we find practical and useful ones, but that are still guaranteed to be more expressive? And this is sort of a general class of functions that you can show. But I think what's most interesting for this particular talk is that the facility location functions are strictly smaller than the sums of weighted coverage functions, which is strictly smaller than the sums of weighted cardinality functions, which is smaller than the sums of concave composed with modular functions, and which is strictly smaller than the deep submodular functions, and which is strictly smaller than all submodular functions. Now, getting back to entropy, we also know that the entropy functions is also, thanks to these additional inequalities, also smaller than all submodular functions. So there's some interesting mathematical problems here, like is the class of deep submodular functions and the class of entropy functions identical, or are there some things that one can do that the other can't, and so on and so forth. So that's an interesting mathematical problem. But there's also an interesting practical problem, which is that it turns out that every single one of these functions in here, despite the fact that we've got a fairly rich class of functions, these are all relatively easy to query in low order polynomial time. And in fact, when you think of everything as a deep submodular function, then it turns out that you can utilize all of the standard deep neural network libraries to come up with very fast expressions of evaluations for submodular functions using GPUs. So it basically makes it such that the query problem that we would have if we were to stick with the entropy, namely the exponential cost of querying just the entropy over a subset of random variables, is no longer here, but we haven't sacrificed expressivity in the class of submodular functions. Okay, so that last sentence is sort of the most critical thing I said about all of these things. So is that basically clear? I wanted to pause for a second and see if there are any questions. So I'll say it again, just in case. So we're interested in identifying a provably mathematically rich subclass of submodular functions that don't have a corresponding cost associated with evaluating them that renders them impractical. Like, for example, the entropy function. Okay. Everybody good? Okay, so if you're paying no attention, then this is a good time to resync. So we also want to talk about optimization goals. So Amin is going to talk about the actual optimization strategies. What I want to talk about is optimization goals. So not only, as I said before, does the submodularity inequality mean that the submodular functions are natural for a lot of problems, but it also means that we can optimize over them. Now, what do we mean by optimizing over them? So we're just going to define the optimization problems. Like one thing we might want to do is find the set that minimizes a submodular function. Right? Now, obviously, if it's a monotone function, then it's trivial to find the minimizer. But this becomes interesting when f is not monotone. All right? Like, for example, the continuous entropy, the differential entropy function is not monotone. Like, how would you find, let's say you've got a differential entropy function defined over 1,000 random variables. How do you find the subset of random variables that minimizes the differential entropy? That is something that ordinarily would require, if you take any arbitrary function, f, then it would require exponential time to come up with to have any chance of offering any kind of guarantee. Sort of the opposite problem is to maximize the submodular function. Again, there's an exponential number of possible subsets. It's actually not so hard to show that despite the fact that you're putting all of these additional requirements on a set function by asking it to be submodular, it turns out there's still 2 to the n degrees of freedom. So submodular functions live in a cone in 2 to the n dimensional space. So it's not like submodular functions live in some low dimensional manifold. So interestingly enough, despite the fact that submodular functions still live in this 2 to the n dimensional space, knowing when f is submodular, this function can be solved exactly in polynomial time, and this problem can be solved approximately in polynomial time. So, and Amin is going to tell you all about that. So other possible things we might want to do is to say, okay, well, what if we don't want to minimize or maximize unconstrainedly? We want to put constraints. So when we're doing convex minimization, we usually have convex constraints. What are the kinds of constraints we might want to use for submodular minimization or maximization? Well, one simple one would be we're only interested in solutions of sets of a certain size. So it's a cardinality constraint. Or maybe we're interested in sets of a certain cost, where we have some other modular cost function W, and the feasible sets become those that are no more than a cost B. This is known as the knapsack constraints. Or we might actually consider, if you think about the power set as a lattice, we might consider a sublattice and ask for the constraints to be within some sublattice of the power set. Or we might ask for the constraints to be such that the subsets abide by some combinatorial object. Like we might want the sets themselves, the feasible sets, to correspond to things like either matchings or paths or trees or cuts or so on some other graph. You might have some other graph that has nothing to do with the submodular function and is there only to express feasible sets. So it would be like combinatorial constraints, submodular max or submodular min. Or we might want the sets to be independent sets in a matroid. So Amin's going to talk all about matroids. These are really interesting and powerful combinatorial objects that are, despite the fact that they're powerful, they can actually, you can show that submodular optimization algorithms can still offer guarantees subject to these constraints. Or alternatively, level set constraints. Like you might have some other submodular function, G, and you say, I want to, say, maximize a submodular function subject to some other submodular function's valuation of the set being no more than alpha. Right? So level set, these are all kinds of things. Now it turns out that this type of constrained discrete optimization problem, again, without making any assumptions about f, are immediately hopelessly intractable. And this is like information theoretically intractable in the sense that they're exponential time. Even if you were to say prove that p is equal to np, these guys would stay in exponential time. They're not even polynomial time verifiable. But when f and or g are submodular, these problems can often be solved with guarantees and often very efficiently and scalably to large data sets. So somehow submodularity, even though that it allows for interaction between anything, even though that there's still 2 to the n degrees of freedom, doesn't prevent you from having efficient algorithms for optimizing them. So I think that's kind of remarkable. There's something, and maybe this is more evidence in addition to the thing I said before, where the submodular inequality has been repeatedly discovered independently. There's more evidence that there's something fundamental going on here. Another interesting optimization goal might be to find partitions. Like you have this big set. Maybe you just don't want to find one set that's good, but maybe you want to take this set and partition it into non-intersecting blocks in a way that whole partition is good. And so like you might say, here pi is a particular partition, so A1 through AM is an M partition, and maybe this function is a valuation of the partition based on the max value of the block in the partition, and maybe this is the min, and maybe this is the average. And so you could think about these kinds of problems where you want to find the partition that maximizes some convex combination of the worst valuation and the average valuation of any block in the partition. Or from a dual perspective, maybe you want to find the partition that minimizes the max valuation plus the average valuation, subject to the convex mixture. And now these are problems that are also solvable. I mean, so in fact, there are these 2 robust cases, like when lambda is equal to 0, where basically it's strictly we're maximizing the min, which is known as submodular fair allocation, and there's also the average case when you're trying to maximize the average, which is submodular welfare. And similarly, when you're taking the min of the max plus average, there's submodular load balancing, submodular multi-way partition. All of these things are sort of, in some sense, the same problem, expressed slightly different. And there's, of course, the mixed case. All of these things, again, you think, well, how could I possibly find a partition out of all of the possible partitions that's good with respect to these objectives? Again, the problem is hopelessly intractable, but when the objective is submodular, it's possible to do it and offer some kind of guarantee. Okay, the last optimization goal I want to mention, there's actually a lot of others that we don't have time for, but oftentimes, data comes in a stream, comes after one of the other. And a lot of, like, for example, when you're doing submodular min, it's assuming that you have all of V accessible all at the same time, and you have memory, and you can just take subsets indiscriminately. Oftentimes, V is very, very big, or oftentimes just the nature of data comes in as a stream. And the question is there are additional constraints, like you can't wait till the end. You can't just wait till the stream to end and then do your offline optimization procedures. You want to have to actually start coming up with a solution as soon as the data starts coming in. So these are called streaming algorithms. And generally they're harder. I mean, they're more constrained. Additional constraints always make things harder. But again, submodularity makes it such that it's possible to come up with guarantees and with scalable algorithms. Okay, those are the optimization goals. The last I want to sort of end, let me just pause for some questions to see if there's any questions about anything we've said at this point. Yep. In which case? In this one? Okay, so what we're trying to do, so we've got a set, right? And we're partitioning the set into subsets, right? And so like we've got M subsets. And no. So what this is doing is basically we're trying to divide the set into subsets in such a way that the division of the sets into subsets is good in some way or another. Right? So that's called a partition. Like if we take a set and we compute its partition, that basically means that there's M subsets that don't intersect with each other, and that the union of all those subsets together is equal to the original set. Right? So like here's an example. I'll give you a good example. So let's say that there's you go to a buffet, okay, and everybody here in the room goes to a buffet, and there's a certain number of food items on the table, right? Everybody gets to choose one hors d'oeuvre. You get a smoothie or something, and then somebody else gets a piece of sushi, and somebody else gets a chicken wing or something, and everybody gets one. Everybody can choose some subset of the pieces of food, but basically once the table is clear, everybody has eaten some subset of the items of food, right? Now, is that a particularly good way? I mean, in some sense, when you go to a buffet, usually it's first come, first serve, and maybe somebody eats all the chicken wings and you don't get the chicken wing, and so you're not happy because you don't get a chicken wing, right? Because somebody else ate too many of them. Well, you can express all of these problems as integer programs. In fact, a lot of submodular optimization, a lot of discrete optimization problems can be expressed as an integer program, but they're usually not the best way to do it, because integer programming is, in some sense, more general and isn't aware of the fact that there are certain properties associated with the problem that mean that integer programming in all its generality is a very poor way of solving this specific problem. And if we can express it instead as a submodular optimization problem, like, for example, a submodular partitioning problem, you can get solutions much more easily. I think that you're asking questions about the optimization problem stuff, and this is going to be addressed to some extent by Amin. What I want to do is just sort of define the kinds of things that we want to do. But you're right that we could always put this into a big integer programming, do a linear programming relaxation, round the solution, and hopefully get a good solution. But generally speaking, you don't have guarantees with that. And number two, also, those types of approaches do not scale to the kinds of problems that we want to solve, where you have hundreds of thousands or maybe even millions of variables, right? But yes, always you can do an integer program. You can do anything with an integer program. Okay, so you could solve world hunger with integer programming if you had a big enough solver. Did you have do you have a question? Yes, go ahead.
So in this formulation, why is there a mixing between the minimum and the average?
So imagine, so take for example, like let's say the max min plus average formation, right? So take this one. The reason for having a mixture is because if you just solve the max of the min, that sort of maximizes the worst solution, right? And then it doesn't really put any preference on any of the other solutions besides the first one. Like once you've got the best worst solution, all of the other solutions could be anything you want. But if you're in addition to the worst solution, to this robust case, you're also putting pressure on having the overall average going up, you might actually get a better overall objective. It really depends on the problem, right? So you can actually, this is what like in this particular case, like submodular fair allocation, there's these two extreme cases. I mean, think about it this way, like in the submodular welfare case, it basically you have a set of goods and you have a set of people, and you want to distribute the goods to the people. And each good can go to one person. And so you want to distribute the goods to the people in an equitable way, right? So submodular welfare, you can kind of think of it as kind of like a Republican strategy, right? Because basically all you care about is the average welfare of the entire population. Each person gets some good, and if the overall society is happy, if the rich are super rich and everybody else is poor, but if the average is good, you're happy. Whereas submodular fair allocation is a more democratic optimization goal, where basically you want to boost the worst case. So like this is right wing, this is left wing, and allows you to mix the two, right? And that sort of gives you a real world example. But does that make sense? Yeah. So, okay, but when do you use which? I mean, it really depends on your problem. I mean, it depends on the application that you want to do. And we haven't really talked that much about applications yet. But okay, so are there other questions? Yeah.
Just going back to that Venn diagram chart you had, so I will see that the cycle-method rank is the only known explicit example of modular function which is not DSF.
Sorry, I didn't quite hear that.
I'm trying to interpret the graph that you had.
So the Venn diagram thing?
Yeah.
This thing?
Yeah, so I see cycle-method rank is the only explicit known submodular function which is not DSF. But it's just like that.
No, it's not the only. It's one that's known not to be. Because the cycle-matroid rank function is not a DSF, interestingly enough. Despite, I mean, you know about cycle-matroid, right? It's very interesting. Because like cycle-matroid ranks on the one hand are very, very simple matroid ranks. And it's known that the cycle-matroid ranks are not all of the matroid ranks. In fact, but on the other hand, there are matroid ranks, like partition matroid ranks, and there are laminar matroid ranks that certain kinds that can't be expressed as cycle matroid ranks. But yes, you can find a cycle matroid ranks that cannot be expressed as a DSF.
But there are other known structured classes of submodular functions that are not DSF. The cycle-method rank is not the only exception.
Yeah, that's a very good question. So this green bit is a little bit unknown territory. So I mean, it's not to scale, or it's not proportional. It's not. I mean, we don't know how big this green thing is on the outside. In fact, it could even be empty. I mean, the thing is, like, I mean, it's a little bit misleading because I mean, you can always like turn a cycle matroid rank into a polymatroid function by grouping things together, and then it's easy to construct one that's not a. So it's anything cycle matroid rank or trivially derivable from a cycle matroid rank, you can come up with examples which are not DSF. But the question is there? I mean, it gets into similar things like matroid minors. Like, you know, so is there any function that's not a DSF that isn't trivially decomposable into a cycle matroid rank? That's an unknown question.
So if you can, I'm just trying to understand why is DSF interesting in the deep net point of view? Are you saying that you use the deep net trading algorithm on a DSF to solve a combinatorial optimization problem? Is that the case?
I'm sorry.
Is it the claim that I can use the deep net trading algorithm on a DSF to solve a combinatorial optimization problem?
No, the claim is that you can use a deep neural network training algorithm to learn a deep submodular function. So there are people who are actually using deep neural networks to try to solve combinatorial optimization problems. I mean, people at Google who are trying to do that. So that's not the claim we're trying to make here. What we're claiming is that the infrastructure associated with training deep neural networks can be used to learn any of these submodular functions. Like, let's say the question is, we want to learn within a class, right? And we want to make sure that we stay within a class so that once we got a submodular function, it's still useful. Still we can use it practically. And all of the infrastructure that exists to train deep neural networks can be trivially modified to train a deep submodular function. And so it means that there's a lot of leverage.
You're still learning a set function.
In this case, you're learning a set function. Now, whether or not you can use that set function to solve some other combinatorial optimization problem, perhaps. I don't know. But that's an interesting question. But
Gradient descent type algorithm can learn a set function.
Yes. Yes, that's exactly right. So, okay, so other questions before we move on? I guess I've got about 15 minutes. So, okay, actually, well, one of the things I wanted to say, I mean, I thought that this community, you know, given it that it's the IT community, I wanted to sort of relate submodular maximization with Kullback library divergences. And so, first of all, before we do that, you know, submodular max can be seen as like a form of summarization. Say that we have some algorithm, like for example, the algorithms that Amin is going to tell us about, that solve this problem. We maximize the submodular function subject to a cardinality constraint. Or alternatively, we have an algorithm that basically finds a set that minimizes the size of A, but ensures that the submodular evaluation is no less than alpha, which is essentially a dual version of this problem, right? So once we've got A star, we can think of A star as a summary. And the reason why we can think of A star as a summary is for the following reason. So we said that F, we can think of F as an information function, right? And so trivially, F of V, F of everything that you've got, is equal to, you know, this is the chain rule, right? It says F of V except for A star given A star plus F of A star. So when we're maximizing F of A star, the residual information of everything that you don't choose is minimized. And so in some sense, A star comprises a summary. What is a summary? Basically, a summary is such that if you've got it, anything that you don't have is redundant, right? It's sort of, you don't need to know that because you already have the critical elements that give you all the information. If this was an entropy function, and you truly were to maximize this, I mean, you could even render this thing 0 if it was the case that V except for A star were deterministic functions of A star. That would render the conditional entropy 0, in which case that would mean that you've got A star gives you everything you need, right? Similarly, when F is any submodular function, A star can act as a summary for the following reason. So what I wanted to do next is sort of relate this idea, this submodular maximization problem, to a Kullback library divergence minimization problem, because I thought this would be interesting to everybody. And so what we're going to do is we're going to do submodular max. We're going to do a submodular max problem on a subclass of submodular functions, which they're basically sums of concave over modular functions, but they're expressed in a particular way such that we often call them feature-based functions. So, and let's say that we're given some large data set. Like, you could think of the data set as a set of images or a set of videos or a set of training samples in a machine learning problem. And we want to choose a summary of the data items. So, you know, using, say, submodular max. And let's say that each data item V is described by a vector of non-negative scores for a set U of features or properties or concepts of each data item. So every data item, you can think of like V, lowercase v as an image, and U could be a set of characteristics of that image. Like it could be whether it has it could be high-level characteristics, like does it have a tree in it, or does it have a building, or does it have a car, or it could be low-level characteristics, like, for example, you know, the Fourier coefficients, or it could be the proportion of green pixels and the proportion of blue pixels, and so on and so forth. All of which can be represented as, in some sense, features. And then for each U, we're letting this value, so that the object is V, the feature is U, and M sub U of V represents the degree of U-ness in object V. Right? And so therefore, when you think about this thing here, M sub U is a vector, it's a length n vector, and you can think of it as a modular function. Right? So like if you're considering a collection of images, and then for each image you have a score, which is how many pixels are green. Or you could have another score, which is the third Fourier coefficient in some sort of Fourier decomposition. So that's basically what this bullet is representing. In natural language processing, you could think of these as n-gram counts. Like if it's a document, M sub U of V could be the number of times that n-gram U occurs in document V. Like if it's about cities, if the word New York City appears frequently, then chances are then the degree of New York City-ness is high in that document. So now if we think about a set of data items and choose a subset X, then M sub U of X is this thing, is basically summing over all items X, and it just sums up the U-ness of all of the objects in X, and hence this is a modular function. And it represents the degree of U-ness in the subset X, but it doesn't have any sort of diminishing returns in this. Like, as we add more, it can only increase, and it never ends up being the case in this modular function that we say, okay, I've seen enough documents about New York City. I want to stop counting the value of documents that have New York City in it. I want to start discounting the value of that concept U. That's what that modular function doesn't do. There's no diminishing returns property as we add items to X. And the degree of U-ness grows additively. If we then instead, to try to sort of model some sort of discount, we can apply a concave function over it so that it grows no longer additively, but it grows subadditively. And in fact, we get the following inequality thanks to the concavity. In fact, what we've immediately done, as we said earlier, what we get is a submodular function. And then if we sum up all of them for each feature, we get what's called the class of feature-based functions. And it's essentially, it's a very standard way of instantiating a submodular function over data items, where the data items are characterized by features in the same space. And it's kind of a useful way because the data items themselves need not even be of the same modality. Like, you could have documents and images, both of which are described by vectors in the same embedded space U. So you can talk about objects of different modalities as long as you can characterize them in the same feature space. Okay. Now, fine. So we've got feature-based functions. Any questions on feature-based functions? So now let's say, and this is where we're going to relate it to Kullback-Leibler minimization. So let's say that we have some probability distribution, again, over features. Like, this is a desired distribution. It's a probability distribution, so it sums to 1, and all of the probabilities are, of course, non-negative. And we adjust our modular functions so that we can define sort of normalized modular weights for each feature. So for any x, m bar sub u is equal to the original m of u of x, but then it's divided by the sum over all features. And so what this means is that this thing here, m bar sub u, can be seen as a probability distribution over features on u. So it's a distribution just like this, right? It's a probability distribution. This is another probability distribution. And it comes from the fact that m sub u of x is non-negative. But it's a different distribution for every possible subset x. So what we've got now is 2 to the n distributions over the features u, 1 for each subset of v. Okay? So I kind of already said this. So m bar of u of x can be seen as a distribution over features u, since it's greater than 0, and summing over u, m bar u of x is equal to 1 for any x. So we've got 2 to the n distributions. Now consider the following. The Kullback-Leibler divergence between p and this distribution. Okay, so we can expand it in this way. So this becomes, the negative entropy of p, and we've got negative the log of, the negative of the sum of p of the expected value of the log of m bar u. But m bar u is itself a ratio, right? So we've got the negative entropy, and we expand out this ratio, and we've got this thing here. And so the Kullback-Leibler divergence is negative entropy plus the log of this modular function. Remember, this itself is a modular function as well, m of x, minus the sum of a convex combination of logs of modular functions. So the whole Kullback-Leibler divergence becomes, let's say that we're, p, if we think of p as a constant, let's say, for example, we're interested in finding the x that minimizes the Kullback-Leibler divergence, right? We want to find the x, we want to find the subset of v, the subset of objects that renders the induced distribution on p as close as possible to this given distribution p here. And so therefore, this negative entropy becomes a constant. We can just ignore it. And we end up getting this quantity here. This is a concave composed with a modular function minus sums of non-negative weighted concave composed with modular functions. So they're both submodular. So we've got a difference of submodular functions. So the Kullback-Leibler divergence immediately becomes a difference of submodular functions. Now, there are actually one of the things that you can do then is to say, well, I can then optimize this directly. There are actually algorithms that optimize the difference between submodular functions. That I don't think you're going to talk about this today, but that's actually one thing. Submodularity, thanks to the properties of submodularity, allow you to optimize differences of submodular functions in a way that's analogous to strategies that people have used to optimize DC functions, difference of concave functions. But alternatively, and this is sort of really where things come home, if we think about a budgeted case, like let's say we're only interested in this is sort of like a quantity value. Like let's say we're only interested in solutions where m of x is equal to b. This is now like a knapsack constraint. Then if we consider this problem, max for all mx is less than or equal to b, or even more trivially, mx is equal to b, then this becomes basically a submodular maximization subject to a knapsack constraint. So submodular maximization subject to a knapsack constraint, which is Amin's going to talk about that very soon, turns out to be something that's identical to Kovac-Leibler divergence minimization in this context. So I think it's very interesting. I was very fascinated when I first learned this, that we relate to the two. Okay, so I'm supposed to end at 3:20, right? So, sorry? 25. Are there any questions about this? So I thought this would be of interest to this group. Okay. I'll just very briefly go over some examples. So given that submodular max is a summarization, one of the things that we've done empirically is we've applied it to various summarization problems, like for example, document summarizations. You've got a large collection of documents you have to read, and is there a way of summarizing them down into a small document that's still preserves the information? And you can argue that document summarization can be cast as a submodular function, and which is what was done. And it turns out that it works really well. And actually, what's also interesting is that many of the approaches for solving document summarization in the natural language processing community ended up instantiating a function that ended up being submodular, but they didn't know it was submodular. And so what they ended up doing is, it was your suggestion, they solved it with an integer programming problem. And it ended up being a dead end because it wasn't possible to get this working on large size problems. And interestingly enough also, that there are two of the standard ways of measuring the quality of document summarizations end up being submodular as well. And that wasn't known at the time. They just developed these as being natural. They said, this is a natural way of judging the summary of a collection of documents. And it wasn't until later was it discovered, hey, those are submodular functions. So this is what I mean. Like, this thing keeps popping up. People come up with something that's natural. It turns out to be submodular. This happened in the machine translation community, in the computer vision community, in the document summarization community, and a bunch of other communities as well. In the computational biology community, actually. So one question is, how do you train them? So it turns out that you can actually train, like the one question was, how do deep neural networks help deep submodular functions? Is by training. Another strategy is by doing a max margin form of training. And I don't have time to really go into this, but suffice it to say that it is possible to, given supervised training data, in the mixture coefficients of a mixture of submodular functions in a way that improves its valuation on unforeseen sets. And this ended up working really well. And at the time, it was actually the state of the art on this data set. I want to also say that this is also something that was applied for choosing subsets of speech utterances to train a speech recognition system without actually losing too much accuracy. And so, like, here's for an example. This is an example of, deep neural network systems are very expensive, right? And here's an example of a Gaussian mixture model. This is a Gaussian mixture model system where you use all of the data, and this is a deep neural network system where you're using only 20% of the data. In fact, here's something with only 10% of the data. Here's 5% of the data. So you can train a deep neural network system by summarizing the data first and get the same accuracy as a Gaussian mixture system trained on all of the data. So basically, it means that you can actually train machine learning systems more quickly by first summarizing training data and then training the machine learning model on the summary. rather than training it on all. Now, the reason why this is the case is because there's a lot of redundancy. Training data for machine learning systems often has prolific redundancy. And the question is, what does that prolific redundancy mean to a machine learning trainer? It means that you're doing wasted computation. You're spending more compute cycles than necessary. Yeah, question? I'm sorry, can you say again?
What do you mean by some order training data first and then training first?
What do I mean by summarize the training data first? So, like, let's say you've got a bunch of training samples, okay? So you collect all this data and you feed it to a machine learning system model, so like a deep neural network or a Gaussian mixture model or something, and you say, train on this data. And so it spends time training on the data, and it comes up with a resulting machine learning model, and then you test it. And you see how well it does. Now what you could do is instead is take this training data, instantiate a submodular function on it, summarize that data down to a small set, like for example, something that's 5% of the original size, and then give that 5% of the data to the machine learning model and say, here, train on 1/20th of the data. But it's not a random subsample of size 1/20th. It's a summarization obtained via submodular max. And then you train on that, and it's 20 times faster because the amount of data is less, but you get, I mean, this is showing that deep neural networks can achieve, I mean, in this particular case, it's showing that with only 1/20th of the data, you get the same performance as this model with all of the data. So it basically means that summarization as a pre-processing step to machine learning problems can often allow you to get to solutions much more quickly than what you would do if you were to instead use all of the data. And the reason for that is because data sets generally tend to be very redundant.
So here, if it's 1% is better than training all the data sets.
Well, 1% is worse. At some point you start losing accuracy, right?
This is the error.
Yeah, this is error. This is word error rates, yeah. These are all word error rates, yeah. So lower is better. You don't need to. Yeah, you don't need to. So it's not like compression. Like one of the things that often comes up when I'm describing summarization is well, doesn't compression do something similar to this? But compression is different. Compression is basically where you're taking the data and trying to come up with some code whereby the original data can be represented encoded in a way that requires fewer bits to store. And once the data has been encoded, it's no longer accessible. Like it's completely changed. You might have variable bit length encoding and so on and so forth. And you can't do anything with that data unless you have a corresponding decoder. But then what the decoder does is it brings it back. It sort of expands it back to its original size. And if it's lossy decompression, then you get some distortion. But the problem is you haven't reduced the size in a form that it's usable. Like once it's compressed, it's inaccessible until you've re-expanded it again. Whereas a summarization chooses a subset. So if it's like a collection of images, a submodular max, a summarization is a subset of images. If it's a collection of videos, a summarization is a subset of videos or subsequence of snippets of videos. You haven't changed the form. So any process you have that uses the original data can still operate on the summary. Because you haven't, and you could actually compress the summary, but the compression ratio probably of compressing the summary would be worse than a compression ratio of the whole thing because you've actually reduced the redundancy in some form or another. And actually, that's something that actually has been tested. And if you try to compress the summary, the compression ratio is worse than if you compress the original. But it's just, they're different things, right? Compression and summarization are two distinct processes. Well, this is one example. So like here's the neural network on all of the data, and then this is the reduction. So this is 20% of the data. So it does get worse. So you're losing some accuracy. But it very much depends on the data itself. It also depends on how well a job you do finding. And this is the problem, right? It's like you've got a data set. How do you find a submodular function that is a good information function for that data? That is a research question. And that is where we've developed and other people have developed, and it's still an open research question, how do you develop techniques to either automatically produce or to learn a submodular function that acts as a good information function for a given data set, where good means that when we summarize it, we don't achieve accuracy losses like this. Right? So this basically says I've got an accuracy loss at 20%. It could mean, the problem could mean that the data is just inherently not redundant, or it could mean that the submodular function that was used for this is not as good as it could be, or it could be a little bit of both.
The second part of the tutorial is going to be all about algorithms. So basically, the first part, Jeff tried to introduce submodularity, some of the definitions. He gave us some examples, properties, and then he briefly mentioned the optimization goals. So the second part is going to be a little bit more about the definitions, and then I'm going to mainly talk about two particular optimization problems, basically submodular minimization and submodular maximization. And then some research directions if you're interested. So the outline of the talk is going to be as follows. As I said, there are going to be some preliminary definitions, submodular minimization. We are going to see basically 2 methods for submodular minimization and 3 methods for submodular maximization. Okay, so we have seen many definitions of submodular functions, and basically this is one that shows diminishing returns in the most intuitive way. And as Jeff mentioned, submodularity has nothing to do with monotonicity. So we can have submodular functions that are monotone, we can have submodular functions that are not monotone. And we say that a submodular function is monotone if adding element is not going to decrease the utility of the function, right? So if A is a subset of B, then f of A is going to be a subset of, then f of A is going to be less than or equal to f of B. And then, we have seen a lot of interesting applications. Jeff mainly talked about data summarization. There are other sorts of applications when people would like to put, sensors for monitoring purposes, network influence. And then Jeff extensively talked about information functions, and many of them are actually submodular. And graph cuts that he also mentioned, there are typical examples of non-monotone submodular functions. These are the submodular functions that they go up and down. Okay. But usually when we want to optimize the submodular function, we encounter some sort of a feasibility criterion. And the way that it is said in combinatorial optimization is that the way that we are going to describe them is as independent system I. Okay, so these are independent system means that these are the set of all feasible solutions for a discrete optimization problem. So one example, a very trivial example, very simple one, is a cardinality constraint or the size constraint. So what here a solution is going to be feasible if and only if the size that we are returning is at most k. A little bit more general set of constraints are partition metroid. So we are going to partition the ground set V into k groups. And then the condition is that from each group we can return at most 1 element. A little bit more general is the metroid independent system, where basically the empty set is a solution. If A is a subset of B, and B happens to be a feasible solution, then A should be also a feasible solution. That is called the down closeness property. And finally, if both A and B are solutions, and B happens to have more elements than A, then it should be possible to find an element from B such that adding it to A is going to stay feasible. Okay? And even more general is when we have intersection of P metroids. So let's see just a few examples, a very simple example. Here is my data set, V. So in the cardinality case, I just want to find 4 elements. Okay? Any 4 element is going to be good. Now, when I have a partition metroid, there are 4 partitions. From each partition, I can only pick 1 element at most. And so when we have intersection of metroids, I might have 4 groups. And my feasibility condition is that from each group, I can have at most 2 elements. So these groups now interact with each other, right? There is the intersection is not empty. So that might be a feasible solution, right? Any group has at most 2 elements. That might be another feasible solution. And there are a lot of independent systems that people looked at in combinatorial optimization, in machine learning, for all sorts of modeling. So as I said, cardinality is probably the most natural and the simplest one. Then the metroid, the intersectional metroids, people talk about p-extendable system, p-independent system, knapsack constraints. And today we're basically going to talk about this type of constraints and the knapsack one. Okay? And there are two sorts of optimization problems that we would like to solve. The first one is the submodular minimization, where we have submodular functions. We want to find a set S that minimizes a function. And we will see that we can actually do that exactly, and this relates to convexity. The other sort of optimization problem that we would like to solve is the submodular maximization, where we also have constraints. So not only I have to maximize f of s, but s should come from a feasible solution. For instance, sets of size at most k. So those problems, we cannot solve them exactly, but we will see that we can solve them approximately, and they're related to concavity. Okay, so in the first probably 20 minutes, I'm going to talk about submodular minimization problem. When we don't have any constraints, we just want to find a set that minimizes a function. And then I'm going to switch to submodular maximization. And there are two, they're completely two different sorts of algorithms that we are going to talk about. That is maximize over all subsets. That we will see. Okay, so you're going to see all, a myriad of optimization problems and a myriad of algorithms.
Can you remember to repeat the question?
So the question was that, would we like to maximize over all subsets? We are going to look at that problem too. Okay, so what is the unconstrained submodular minimization problem? I have a set V of size n, that is my ground, so I want to find the set S that minimizes f of s, right? There are no constraints. There are 2 to the n feasible solutions, right? So the main question is, can we find the minimizer without checking all the feasible solutions? Can we find a polynomial time algorithm? And the beauty of submodular minimization is that that can be done. And that is one of the main breakthroughs in submodular minimization. And that is the main connection that we are going to make between a combinatorial problem and a continuous optimization problem. Okay, so basically, probably you have seen a lot of relaxation of the problems. You have a combinatorial optimization problem, then you write down a linear program, try to basically maximize or minimize that linear program, right? We're going to do the same thing here, but we are going to basically, the relaxation we are going to take into account is not linear, it's going to be a convex. So we have our discrete optimization problem. Instead of solving this discrete optimization problem in the discrete domain, we are going to look at a continuous relaxation that can be evaluated. Once we go to the continuous domain, there are a lot of algorithms. We try to use some of those algorithms in order to find the minimum of the objective function. But the minimum can be a fractional solution, right? So what we have to do at the end is that we have to round it back. We have to come up with an integral solution, because our problem primarily was a combinatorial problem in nature, right? I have to return a set S. I cannot return a fractional solution. Okay, so how we are going to do that for submodular minimization? The first thing is that, and Jeff mentioned a little bit in his part, the first very simple thing that we are going to do is to represent every subset by a vector. Okay, and the vector is going to be a characteristic. It's going to be the characteristic vector of the set. For instance, the empty set is going to be represented by 0, 0, 1. The set that contains only element 1 is going to be represented by 1, 0, 0. The set that contains, for instance, 1, 3 is going to be represented with 1, 0, 1. So I have a ground set of size V. I can represent every subset with a vector that contains only zeros and ones. And the vector has to have only size n, right? So that is my vector. And I know by submodularity, submodular function puts a value on the corners of this cube, correct? So I know those values. The question is, what is the value inside the cube? That is where the extension comes into place. So the problem that we are trying to solve is find a subset S, and equivalently, is basically is finding a vector x from 0, 1s to the n that minimizes f of x. Right? I just changed the representation. Nothing has changed. Now, instead of solving this problem that is still combinatorial, I'm going to solve an extension. I'm going to come up with a function that is continuous, and instead of looking at only 0, 1 vectors, I'm going to look at all the intervals, all the points in the cube, and try to solve that problem. And then hopefully, when I find a solution to that problem, I can round it. Is the outline clear, what we are trying to do? Okay, so what is the extension that we are going to use? Actually, that is called a Lavage extension. And for any vector x, first of all, we are going to define t of theta. That is going to be all the elements in the ground set such that x sub e, the coordinate that corresponds to the element e, is greater than or equal to theta. So that is just a simple example. I have 8 elements. These are the values of these elements at a particular point x. Okay, so that is x1, that is x2, x3. And then I pick and selected theta, and then all the elements whose height are above theta are going to be selected in my set, t theta. All the ones that are not going to be selected. Okay? So based on the value of the theta, I'm going to see different sets. Correct? Now, the Lavage extension is nothing but taking the expected value over f of t theta when theta is randomly selected from 0 to 1. It's nothing but an expectation. Uniform. Yes? Sorry, the
Originally set f is a set function.
yes.
So now how do we define f?
This one?
Yeah.
This is still a set function. T theta is actually a set, right?
Okay, I see.
Right? So it is a set. So these are all the elements whose value are above theta, right? Some of the elements are going to have that. And then I'm only going to take the expectation over the uniform distribution when theta is chosen uniformly from 0 to 1.
So f is a set function, right? So the first diagram that you have, so these are the evaluations of the singleton set, is it?
No, these are at the particular, so x1, x2, x3, right?
Singleton, f of the singleton.
So f of the x1, f of the x2. It's xe. Okay, so this is, so at the particular point, these are coordinates, right? And x of e, so at the particular point x of e, either it is greater than theta or less than theta. These are, there is no value yet. Is that clear? The value kicks in here when I take the expectation. So this is a 1x. The first coordinate has this value. The second coordinate has this value. The third coordinate has this value. And that's it. Any other questions? So it is nothing but the expectation. And it is defined for any x between 0 to 1. So let's just calculate what it is for a very simple example. Let's assume that my v is E1 and E2, and my x is 0.5 and 0.7. Okay? That might actually clarify what this multilinear extension is at that particular point. Okay? So with probability 0.3, basically if theta is between 0.7 to 1, I'm not going to pick any set. Correct? So that is the probability times the value. And then when theta is between 0.5 and 0.7, I'm going to pick only E2. Right? So the probability is 0.2 times the value. And then if theta is between 0 to 0.5, then I'm going to pick both E1 and E2. What's the chance? If it is uniform, it is 0.5. So that is going to be the value, the Lovasz extension at this particular point x. Is that clear now? Now let's look at another very simple function. So this function is basically the minimum of 1 and the cardinality of S. It is basically always 1 except when S is the empty set, right? And if you go through the math, you'll see that the Lavage extension is going to be the infinity norm. Another interesting example, if you have a graph G, and then if f is a cut function, then the Lavage extension is the total variation distance. Okay, so these are a few examples. Now, we want to maximize the submodular function. Basically, we want to minimize the submodular function. We want to minimize the Lavage extension. And the way that we are going to do that is actually related to the submodular polyhedron and base polytope that Jeff a little bit talked about. So what is a submodular polyhedron? It's basically all the x's in Rn such that they satisfy this set of inequalities. So there is one inequality for any subset there. Okay, so there are exponentially many inequalities. And all the x's that satisfy these inequalities are going to be in my submodular polyhedron. So in a three-dimensional case, this thing is going to be my submodular polyhedron, for instance. Now, what is the base polytope? The base polytope is exactly the submodular polyhedron when the last inequality at point V, when I have all the elements, instead of inequality, it should be equality. So it has one less dimension. And that is going to be the base polytope. Okay? And the reason that submodular minimization can be done is because of exactly the properties of this base polytope. So we'll see now. So a very interesting result is the following. If f is a submodular function, that was my Lavage extension, which is the expected value. It turns out it is going to be the maximization over all the points in the polyhedron, which is going to be the maximization over the base polytope of linear functions. Okay? So I have all these linear functions, and the only thing that I have to do is to maximize them. So that immediately shows, because this is maximization over a set of linear functions, f of L, in this case, is going to be convex, right? It's going to be like a function like this. It's a non-smooth convex function, but nonetheless, it is a convex function. Now, okay, this is a convex function, but it is convex, but it's not still clear that you can actually do this maximization. And what turned out to be true is that you can actually do it using a very simple greedy algorithm. And the greedy algorithm, what it does, morally, is that it takes a coordinate and increases that coordinate until it hits one of the boundaries, and then switches to the next coordinate. It increases until it hits another boundary, and switch. So basically, what we are going to do is that we are going to sort the coordinates, and then AI is going to be basically the first I coordinates, and Y is going to be f of AI minus f of AI minus 1. So that procedure can be done in n log, sorting can be done in n log n. So basically, this maximization can be done in n log n. All right? Moreover, this is going to be, it's a non-smooth convex function. But still, we can minimize them because these y's are going to be the subgradients. Meaning that, if you have a non-smooth convex function and you have the subgradients, you can use, the first order methods in order to minimize. But the connection goes both ways. So as I said, this is a Lavage extension. It is non-smooth. Okay? In 2 dimensions, that is a Lavage extension. And the function is going to be convex. At any set function, the Lavage extension is going to be convex if and only if the function is submodular. So that's a very strong connection between submodularity and convexity. The Lavage extension is defined for any set function, but it is going to be convex if and only if the function is submodular. And one can, it is not hard to figure out that basically the Lavage extension is a convex closure of F. Okay, so once we know this fact, once we know that it is actually a convex function, it's a non-smooth convex function, we can find the subgradients, then there are all sorts of convex optimization methods that we can apply in order to minimize. Okay, so now we can minimize the function. The question is, what is the rounding? We might actually get into a fractional point, but it turns out the rounding is also trivial. Basically, what you end up is going to be a corner point. No rounding is needed. In other words, you're going to pick all the entries such that xe is going to be greater than or equal to 0. Very simple. So what it means is that the minimization of this problem, which was combinatorial, is going to be exactly the minimization of this problem, which was which was continuous. And the problem on the right-hand side, we can do it. We can do it in polynomial time. And okay, there is a slightly better algorithm now, but 2-3 years ago, the best algorithm that was based on cutting plane algorithm had this, the time complexity, which was basically n cubed times t, where t is the time to evaluate the function f on any set S, plus n4. So that is the best theoretically known result. Okay, it's slightly better than that now. I think now we can shove, instead of n cubed, it is a little bit better. But I don't know of anyone who actually implemented the algorithm. So the constants behind these algorithms are huge. No one can actually run the algorithm. So let me just tell you about a more practical algorithm for this problem, which is, so that was one thing. The other thing is that much faster algorithm exists when you have special class of submodular functions, and that is some of the works that Jeff with some of his students did in the past. Okay, what is a more practical algorithm to use? It is basically the minimum norm point, and this is a very simple optimization. Okay, simple to explain optimization algorithm. Well, what we are trying to do is to basically minimize a quadratic function, a very simple quadratic function, subject to the base polytope constraint. Okay? And let x be the optimal solution. The optimal solution is going to be unique because that is a strictly convex function, right? And x star is basically called the minimum norm point of the base polytope. So that problem, we can do it. And then what is interesting is that given this optimal solution, we can form two sets. A minus, which are going to be all the entries, all the elements from the ground set, such that x star of E is going to be less than 0. And A knob is going to be all the ones that are less than or equal to 0. So clearly, A minus is going to be a subset of A knob, right? Because inequality here is weaker. And also, x star of A knob is going to be equal to the x star of A0 because A0 only has elements that have value 0, right? So in terms of solutions, they are going to be equal. Now, what we can show is that f of A minus, which is equal to the f of A star, is going to be less or equal to f of A for any A in the ground set. Basically, A minus is the unique minimal minimizer, and A knob is the unique maximal minimizer of f. So we found a solution, and there is going to be a lot of solutions, right? Because, again, it's a non-smooth convex function, so there are going to be a lot of solutions in between. All of them are the minimizers. 2 of them are easy to find. So the problem is solved. There is one caveat, and the caveat is to analyze the algorithm. Actually, to the best of my knowledge, there is no polynomial time algorithm. So the best known result is a pseudo-polynomial time for this minimum norm. But in practice, the algorithm works much, much faster than the cutting plane. Okay, so how about constraint minimization, where I want to minimize f of A should satisfy some feasibility constraint. Let's say A should have at most k entries, k elements. So it turns out the problem in general becomes intractable. You cannot even approximate the problem. But again, for certain submodular functions, so the ones that are not fully curved, and we have not talked about them, or for the ones that the curvature is actually away from 1, so they are like modular functions or closer to modular functions, again, we can actually solve these problems using very efficient combinatorial algorithms. And that is, again, some of the work that Jeff did with his student. Okay?
So here, the cardinality constraint is the maximum the constraint of the maximum cardinality.
Yeah. It means at most I can pick k elements, for instance. There are also other kinds of constraints. You can say that it's a metro constraint or exact cardinality constraint. There should be exactly k points. None of them can be solved in general. They're very intractable. Okay. So now, for the most of the presentation, I'm going to talk about submodular maximization. But let me know if there are any questions up to this point. Yes?
This gives out the intuition to the base polytope.
Right. So basically, so they're all. So the polymatroid and polyhedrons, all those things are extremely related to submodularity. Okay, and so the base polytope, in particular one, it was the one that among all the inequalities, it had basically the last inequality should have been equality. So, and the optimization over that polytope in particular is easy. So greedy algorithm works. Yes. And okay, so there are properties of the base polytope too into it. Do you have any better intuition of, in one sentence?
In one sentence, no.
Yeah, so, okay, offline we can dig into, okay? Very good. So what is a constraint submodular maximization? Now we are going to talk about a completely different problem, right? So we,
Here's one thing. It's analogous to the base of nature.
I think it is more confusing now. Okay, so what is a submodular maximization problem? I have a utility function, and that is, most of the applications that Jeff talked about, we are trying to maximize the utility function. And we have some sort of constraints, okay? And we all, as usual, we assume that there is an oracle evaluation. For any set S, there is an oracle that tells me what is f of S. So the problem turns out to be NP-hard even when we have a cardinality constraint. But it can be solved approximately, and we are going to see a lot of algorithms that can solve this problem approximately for various type of constraints. So basically, there are three types of algorithms. The simplest one to explain are the discrete and deterministic algorithms. These are the first that we are going to see. Then we are going to look at the randomized algorithms. And again, we are going to see the continuous relaxations, exactly the same way that we had for the minimization, but a different sort of relaxations. Okay, so what is the most natural algorithm that we can try in order to maximize a submodular function? Probably the simplest one, and the one that I'm sure most of you can think of, is the greedy algorithm. And the way that it works is that I start from an empty solution, and then I just go over all the data points and check, is there an element E that I can find such that adding that element to my current solution is feasible? I'm not violating any feasibility constraint, and it's going to increase the utility. If such elements can be found, I'll take the best one. Okay? Very simple algorithm. And return that set. So the question is, does it work? Now let's just, for an exercise, let's instantiate this greedy algorithm when the function is monotone, so adding elements is going to increase the value of the function, or is not going to decrease the value, at least. And I have a cardinality constraint, so I have to pick at most k elements. So in that case, I'm going to pick k elements, right? Because adding elements is not going to hurt. So what is the greedy algorithm in that simple setting? Well, I start from the empty solution. I go k times over the data, over the ground set. And at each iteration, I find an element E such that it maximizes the marginal gain. Basically, it maximizes, so I find an element E such that it maximizes my gain with respect to what I have already picked. And then after k iterations, I'm going to return a set of size k. Clear how it works? It's very simple, right? Now, here is a very nice result that if the function is a monotone submodular function and subject to a cardinality constraint, then the greedy algorithm is going to provide 1 minus 1 over E approximation guarantee. It's 63%. Can anyone think of a better algorithm? Any idea? There is at least one. Sorry? You can try 2 at a time. Is it going to be provably better? So it turns out that it is NP hard to get a better approximation guarantee. So I'm just checking because I don't know. Probably, you guys know, and then you solve an NP hard problem. So every time I give a talk, I check. Okay. So far, apparently, no one has a better algorithm. And actually, you can show that information theoretically, you have to make exponentially many queries in order to get a better approximation guarantee than this. And the number of oracle evaluation is going to be basically k times n. You have n elements, you go k times over the data, so the number of evaluation is going to be k times n. As k goes, yeah. So it is 1 minus 1 minus 1 over k to the k. And that is what it is. Okay, so now let's look at, very similar problem, but a little bit more general. The constraint is not a simple cardinality constraint. I have a knapsack constraint. So it's a linear constraint where I want to maximize my function, but I have to make sure that I'm not exhausting my budget B. So when the elements have the unit cost, it's exactly the submodularity, right, with cardinality constraint. It is a little bit more general. Can we solve this problem? So of course, the greedy algorithm is not going to be a very good algorithm because it doesn't care about the cost of elements. It just cares about the utility of the elements. So of course, it's going to do a very bad job. A natural idea is actually to look at a cost-sensitive greedy algorithm, which basically is going to balance between the utility and the cost, right? It turns out that this algorithm is also not going to do well. But here is a very interesting thing. If you combine the two algorithms, run once the usual greedy, run once this cost-sensitive greedy, return the better, it gives a constant factor approximation, which is going to be 1 minus 1 over E, 1 over square root E of the opt. It's not the best approximation guarantee. Actually, the best approximation guarantee is going to be 1 minus 1 over E, but the algorithm is much more complicated, and the running time is basically n to the 5. But we know that there are polynomial term algorithms that do better. But this is a very simple deterministic one. In the hardest case of what? To do what? To better than this approximate 1 minus 1 over E? Yeah, because it is strict generalization of the. Then, okay, I'm not sure what the question is then. Yeah. Oh, that's okay. Very different question, right? So you can, when you run these algorithms, you usually get better than 1 minus 1 over E. And then there are all sorts of research questions why we get better. Probably the function has more structure than submodularity. And one of the way actually to model the structure is through this curvature that I talked about, right? How close the function is to a modular function. And once you have, once you quantify these characteristics of submodular functions that can be done in linear time, you can provably get better approximation guarantees. But for general submodular functions, with that, to the simplex, not that I know of. Okay, let's talk offline. Okay, now how about the metroid or intersection of metroids? It turns out that the simple greedy algorithm is going to work in the following sense. It gives constant factor approximations, but they are not the best constant factor approximation. And we're going to see how we can actually get better than this. Okay, so in particular for the metroid, we are going to see that we can basically get exactly 1 minus 1 over e, but then we have to do a lot of work. Okay, how about non-monotone functions? Okay? It turns out, greedy algorithm obviously is going to do pretty, poorly. So if this is my ground set, let's assume that the value of E1 is 1 plus epsilon. The value of any subset that contains E1 is going to be 1 plus epsilon 2. Okay? It's a trapping element. If you have E1, the value is going to be 1 plus epsilon. But the value of any subset that doesn't contain E1 is going to be the cardinality. All right? So what does the greedy algorithm do? It's going to pick E1 and it's going to get stuck. Right? What is the best solution here? Any guess? Pick anything but E1. Right? So n minus 1 is the best. This is 1 plus epsilon. So it can do arbitrarily. All right. So running greedy once is not going to work. What is very interesting is that actually you have to run greedy twice in the following sense, which is very, very intelligent. It is called the double greedy algorithm. So we are going to start with two sets. One is A knob that doesn't contain any element. The other one is going to be the B knob that contains all the elements from the ground set. And then we are going to do the following thing at each iteration. There are n iterations, and at each iteration I'm going to do the following things. I'm going to check how much do I gain if I add EI to AI minus 1. Okay? So that is going to be xi. I'm then going to check how much do I get by removing an element from bi minus 1. That is going to be x, that is going to be yi. Then, if xi, adding is better than removing, I'm going to add the element to ai and keep bi as it was. Otherwise, I'm going to the other way. So this is an example. So again, A0, we can represent it by all 0 vector. A B0, we can represent it by the all 1 vector. And then at each iteration, we are trying to match. Either we remove elements or we add elements to, right? So after ith iteration, the first I coordinates are going to be equal when we do this. So after n iterations, an and bn are going to be exactly the same sets. And what is nice about this algorithm is that these guys basically showed that it gives 1/3 approximation guarantee to the unconstrained submodular maximization. However, it's not the best approximation guarantee. There was a paper a year before that showed that the best approximation guarantee, they couldn't come up, but they showed that it is NP hard to get better than 1/2. And we are going to see how we can actually get 1/2, but with a different idea. Related, but different. Okay, so it was unconstrained submodular maximization when the function was non-monotone. How about the cardinality constraint? So what we can do is, again, run greedy algorithm twice, but in a different way. So the way that we are going to do it is that we are going to run greedy get a set Si. And then we are going to run the unconstrained greedy, like the double greedy algorithm on Si. We are going to get another set, which is a subset of Si. We call it Si prime. And then we are going to remove all the elements that the greedy picked from the ground set. We do these operations twice. Pictorially, this is it. I have a set V. I'm going to run the greedy, it's S1. I'm going to run the unconstrained maximization, it's S1 prime. Remove elements, do greedy, unconstrained, remove, and that's it. And then the best of this, I will return. Very simple, right? And again, it was shown that you can actually get 1/7 approximation with this very simple algorithm. It was shown that better than this approximation. It's not the best approximation one can get. Better than this 0.49 is NP-hard. Okay. How about p-metroid? You got the idea. So we start from the full set. We run exactly the same thing L times. And it was shown that if L is equal to p plus 1, the approximation guarantee is going to be 1/3p. You can actually improve the approximation to 1/2p. You can even run it fewer times, get better approximation guarantees, and that is the best known approximation guarantee for maximizing a non-monotone submodular function subject to intersection of p-metroids. And these are all the results that we know of. If we want to run a deterministic and discrete algorithm. And these are the best known results, which are tight. Okay. So how can we get better results or faster results? So the greedy algorithm has to go multiple times, right, over the data sets. And that is very often not possible. Is it possible to actually accelerate the greedy algorithms? And that is the idea of the randomization. It turns out that randomization is not only going to accelerate, very often it's going to give us better approximation guarantees. So let's start again with the simplest problem. So I have a monotone submodular function, and I have a cardinality constraint. The algorithm of choice was the classical greedy algorithm that goes k times over the data, each time finds the best element that maximizes the marginal gain. How can I randomize the algorithm? There is a very simple trick. Let's instead of looking at all elements from the ground set, let me subsample them. Okay? I forgot it should be n over k. Okay? I subsample basically n over k elements from the ground set every single iteration, uniformly at random. Then at each iteration, the number of evaluation is going to be n over k. I have k iterations. The number of total evaluation is going to be n. Right? So it's linear. In linear time, I can basically run this algorithm. The question is, what is the approximation guarantee? And it turns out that for this very simple randomized algorithm, the approximation guarantee is 1 minus 1 over e minus epsilon. It's tight. So the usual greedy algorithm gives us 1 minus 1 over e. The total number of function evaluation is going to be k times n. This simple algorithm gives us 1 minus 1 over e minus epsilon, but the number of evaluations is going to be independent of k. Okay? So, and that is, if you run it on a, very simple case, the specific of the simulation doesn't matter. It's, an instance of a submodular function. So that is a greedy algorithm. The running time, as you increase the size, as you increase k, and these are all the versions of the stochastic greedy algorithm with different epsilons. So that goes up. All the other ones look like nothing. And these are the values that you get. So that is a greedy. All the other ones are pretty much like greedy, right? The total number is n log 1 over epsilon. At each iteration, the number of evaluation is going to be n over k. log 1 over. It is an expectation result. It was very recently shown that if k is greater than or equal to log n, it's with high probability. It's not with us, it's with Jan Singer in Harvard. Okay? So not only in expectation, and we're going to see, okay, all the results that we're going to see are going to be in expectation. This particular one is going to be also with high probability. Good. So how about unconstrained submodular? Right? I just talked about constrained version, but okay, unconstrained submodular maximization. How can randomization help there? Here is a trivial algorithm. I don't have any constraints, so I can't pick any set. Let me pick a set completely at random. Well, basically, I pick any element with probability 1/2. Does that work? Any idea? It turns out it works, even though it is completely surprising. So the expected value of f of s is going to be at least 1/4 of the optimum. That is very sick. Randomly, you pick elements with probability 1/2. It's unconstrained version. Gives you 1/4 approximation guarantee. Okay, but it's not better than what we had before, right? For the unconstrained version, we had 1/3 approximation. That was a deterministic algorithm. Now, is it possible to combine the two? So that was the double greedy algorithm that gave us 1/3 approximation guarantee. Can we combine the two algorithms? It turns out we can do, and here is one way. So what we are going to do is that instead of looking xi's and yi's as values, we are going to look at them as probabilities. The first thing that we have to make sure is that xi's are non-negative, right? So basically, I'm going to make xi prime, which is the max of 0 and xi, yi prime, which is the max of 0 and yi. And then instead of deterministically picking whether I should add an element or remove an element, I'm going to probabilistically do it. So with probability proportional to xi prime, I'm basically going to add an element to my AI. And otherwise, I'm going to remove an element from bi. Okay? It's the same double greedy algorithm, but in a probabilistic sense. And what is very interesting is that this algorithm gives us 1/2 approximation guarantee, which is tight. So very simple. It was an open question for many, many years. And these guys basically solve it with this very simple and elegant algorithm. Okay. So how about constraint version? So again, I have a non-monotone, but a cardinality constraint. What can I do? Well, the greedy algorithm obviously didn't work. Let's robustify the greedy algorithm. Let's make it less greedy. One way to do it is basically, what greedy does is that it goes for the best element. And that is bad when the function is non-monotone. Instead, what we have to do is that we look at the top k, okay? And then pick one of the top k at random. Not exactly top k, because in the top k you might have negative. So those negative elements are not going to be good, right? So they're not going to increase the value. So among the at most top k elements that all have positive marginal gains, I pick one of them at random. How does that work? Well, it turns out it gives 1/e approximation guarantee. What is very interesting is that this algorithm is oblivious to whether the function is monotone or not. If the function happens to be monotone, it gives exactly 1 minus 1/e. If it is not, it gives 1/e. So I think that is the first instance of an algorithm that I know of that is completely oblivious to whether the function is monotone or not. It always gives a good result. And it can also be accelerated using this subsampling idea. Basically, you can do 1/e minus epsilon in linear time. Okay? How about the p-metroid? So remember, we had this repeated greedy algorithm, right? For the p-metroid, we had to run the greedy, remove the solution, run the greedy again, remove the solution, etc. Now we can use basically the same idea. So what we are going to do is very simple. We're going to subsample with probability 1 over p plus 1 and run greedy once. Okay, so subsample the elements, run greedy on those elements, and then in expectation, it's going to give us something very, very good. And these are some experimental results about how it works. In practice, this is the best repeated greedy algorithm if you adjust all the parameters correctly. So everything is normalized, the utility and cost. This is the algorithm that I just explained, the sample greedy. You can actually, you can boost the performance of the sample greedy algorithm by just run it 4 times, pick the best solution, right? So in that way, you basically recover 95% of the utility with 1% of the cost. It's really fast, and it works pretty much like the best deterministic algorithm that we are aware of. Okay, and then so if you use the randomized algorithms, basically you can get this tight approximation guarantee, and this 1 plus p plus 3 is basically very close to tight. We have also lower bounds that show that you cannot do much better. Okay. Now what we are going to see is, again, how we can look at submodular maximization from the continuous relaxation point of view, the same way that we looked at the minimization problem. But before doing that, let me know if there are any questions. It's going to become, the algorithms are going to be different now. Okay, clear? Very good. So for the minimization, we looked at the convex closure, right? We were trying to minimize, so convexity was a good thing, right? Because we know how to minimize convex functions. So the first idea is to look at the concave closures. It turns out computing the concave closure is very hard. Convex closures were simple. They were the Lavage extensions, et cetera, et cetera. Concave closures are very difficult to compute. So we are not going to look at those. Instead, we are going to look at another relaxation that has some strong connections to concavity. And this is the multilinear extension. So it's a multilinear function. It is also an expectation, but it's a different expectation. Okay? So what is the expectation here? So the multilinear function at any particular point x is going to be the expected value of a random set R. Okay? And what is the random set R? Where any element in R is going to be selected with, so any element E is going to be selected with probability xe independent of others. It's a random set. Okay? And then we are taking the expected value. So if I expand this, it is going to be this sum. So I'm going to go over all subsets of the ground set. For any particular A, the probability that I see A is going to be the products of xe's. And I don't have some of, and A doesn't have some elements. The ones that are not going to be in A, I'll pick them with probability 1 minus xe, right? So they're chosen independently of each other. That is the value, so the whole thing is going to be the expected value. Okay? So here it should be the expected value of f of Rx. There is a typo here. Now, let's put Lavage extension and the multilinear extension neck to neck. So in the Lavage extension, we were picking a threshold uniformly at random. Everyone above is going to be selected. Everyone below is not going to be selected. In the multilinear extension, instead, we are going to look at every single entry by itself, and we are going to flip a coin. With probability x1, this guy is going to be selected. With probability 1 minus x1 is not going to be selected. With probability x2, this guy is going to be selected. With probability 1 minus x2 is not going to be selected. So it's a different random process. What is the relationship? When you can show that the Lovasz extension is going to be always pointwise below the multilinear extension. And that is actually a result that is much more profound than this. You can show that the Lovasz extension in some sense is going to be the minimizer or all sorts of expectations where the probability distribution is going to agree with the marginals. Okay. The good thing is that this time the multilinear extension is smooth and differentiable at any point. It is a multilinear function. It means that if you look at the second derivatives, it's going to be 0. It's basically, if you look at the Hessian, all the elements on the diagonal are going to be 0. All the off-diagonal elements are going to be less than or equal to 0. Third, this function is going to be concave along any positive direction. Okay, so if you have a vector D that has all positive entries, and you go towards that direction, f is going to be a concave function. But the function is not concave all over the place. If you look at the Hessian, right, point-wise, it is less than or equal to 0. So it is not a negative definite function. And if f is monotone, then along any positive direction, the function is also going to be positive. So now what we're going to do is exactly the same thing that we did for the minimization. We are going to use the multilayer extension, but the problem is that the function is not convex nor concave. It has some connections, but it is not general concave function. So we are going to solve this non-convex problem. The solution is going to be fractional, so we have to round the solution this time. Find a near optimal solution. Once we find a near optimal solution, we have to round it. Okay, so the procedure is going to be more complicated. Okay, so instead of solving this combinatorial optimization problem, what we are trying to solve is a continuous relaxation. Well, instead of, before we had to go over all feasible solutions, now we are going to look at the natural relaxation of the feasible solution. And a very natural relaxation is that we are going to look at the convex hull of all the feasible solutions. Okay? So that is a polytope. I want to maximize a non-convex, non-concave function over this polytope. And this is an instance of these functions, this multilinear extension. So you see, if I go along the positive direction, the function is concave. If I flip, I go along the negative direction, the function is actually convex. So it has saddle points. Now, can we do that? So what is the simplest myopic first-order method for maximizing continuous function? What would you do if you have a function you want to maximize? Any idea? Yeah, gradient ascent. Okay, so the question is, can we use gradient ascent, get some solution? Okay. So in gradient ascent, basically, we have to set a parameter t, the number of rounds, and then a learning rate that is mu t. And then what we are going to do, I'm sure most of you know, we are going to update our current solution with going a little bit towards the gradient. And then we might be outside of the polytope, so we have to project it. And we do it t times, pick one of the solutions at random. There are many other ways actually to do it. You can pick the last solution, you can pick the an average of of all solutions, many other ways. So what we can show is that if you correctly identify the rate, which is 1 over square root t, after 1 over epsilon iterations, you can actually solve the problem. You can get a 1/2 approximation guarantee. Okay? Even though the function, it's not convex, it is not concave, this simple procedure is going to give you 1/2 approximation guarantee. Is it the best? Not really. So the main breakthrough is actually this continuous greedy algorithm by von Drack. It is like an algorithm, but it is not really in the format that I'm showing. So how does the algorithm work? You start from the origin. And then it's like a particle moving, okay? You're basically solving a differential equation. So in the first step, so that is where the gradient is going to go. So if you wanted to follow the gradient, you will go a little bit along this direction. Instead, what this continuous greedy algorithm does is that it finds a point, one of the corner points, that is most aligned with the gradient and follows that direction. So it's going to go along this direction a little bit. Okay? So it finds that point V, which is simply a linear program. So instead of projection, we're using a linear program. Now, how much you go, the rate at which you go along that direction is going to be dictated by y. So x is, so yt is going to be at the rate of this. Okay, so you start from 0, you go, you solve this differential equation, and then the solution that you're going to return is y1. Is that clear? The question is, what is the approximation guarantee of this algorithm? As I said, per se, this is not an algorithm you can run on your computer. You have to solve a differential equation. So you have to discretize this. But let's assume that we can actually have these infinitely small step sizes. You can solve this differential equation, go along this differential equation. So it turns out that the value that you get at 1 is 1 minus 1 over the approximation guarantee of the opt. Okay? For any solvable polytope, meaning that if you can solve this linear program, if you can find this point V, okay, then running this algorithm is going to, at point 1, is going to give you 1 minus 1 over the approximation guarantee. So how about the non-monotone case? Well, it's basically the same algorithm, but because it is non-monotone, you don't have to be as aggressive towards the direction that you're going. You have to actually slow down a little bit the rate, and then again return your solution at point 1. And what was shown is that this measured continuous greedy algorithm is going to provide 1 over E approximation guarantee. Now, can we run these algorithms? Basically, there are two practical issues. First of all, they rely on finding the gradient and solving this linear program. Is it possible to find the gradient? That is the first question. The second is that, well, on my computer, I don't know how to solve this thing. This is an infinite small step size. I have to discretize it. There are entire books written about how to discretize differential equations, and we're going to see one of instantiation of those. Okay? Now that is my multilinear extension. Again, I'm sorry for the typo. It should be expected value of f of Rx. But the main point is that it is going to be this huge sum. There are exponentially many terms, right? It goes over all subsets. Evaluating the multilinear extension is not possible in many cases, let alone finding the gradient. So finding the exact gradient is going to be computationally prohibitive, but finding an unbiased estimate of the gradient is going to be easy. How can I do that? Well, the only thing that I have to do if I want to find an unbiased estimator at coordinate I sample a random set, add EI to it, remove EI from it, and look at this difference. That is going to be an unbiased estimate of the gradient. Good. So I have an unbiased estimate of the gradient. Does the algorithm work? So the first idea is that, well, let's look here, use an unbiased estimate of the gradient instead of the exact gradient in the algorithm, right? It turns out it's not going to work. It's going to diverge. This linear program is very sensitive to the variance of the unbiased estimate. And technically, because the expected value of argmax is not equal to the argmax of the expected value. The second idea that people used was that sample a lot. So I have unbiased estimates. I can sample a lot of these unbiased estimates and basically use the Chernoff bound in order to have a very, very precise estimate of the gradient. The third idea is basically use the momentum. The one that we are going to use is that this is an unbiased estimate of the gradient. We are going to look at the moving average. Okay? So the estimates that we are going to use are basically dt, which is a weighted average of my previous estimate plus the current estimate that I got. So let's see how the algorithm, the full detail of the algorithm, when we discretize it and using unbiased estimates of the gradient works. So we initialize from x0 and d0 at the origin. At each iteration, I just form this estimate, dt. And then instead of putting here the unbiased estimate of the gradient, I'll put dt. For the discretization, it's a very simple discretization. I'm going to use basically a constant step size, which is 1 over t. It's very, very simple. So that is a stochastic continuous greedy. And then you can show that if you choose the parameters correctly, then the value that you're going to get at the tth iteration is going to be 1 minus 1 over e f of the optimal solution. That is one way to do it, but certainly not the only way to do it. Okay. We can do exactly the same thing for the measured continuous greedy algorithm. Exactly the same discretization, exactly the same estimate of the gradient. And then you can show basically the same result, that you get 1 over e approximation guarantee at the rate that is cubic in epsilon. So this is an algorithm you can run on your computer. So now we're going to look at, so we get this approximation guarantee. Certainly here, the x that we are going to find is fractional. Okay? Now what should we do? We want a set S. We want an integral solution. So here, you're going to find a point x in the polytope. The first thing that we are going to do, so that is my x in the polytope. I need a solution here. So one of these points, right? I cannot return a solution that is here. The first thing that we are going to do is actually independently pick elements, right? R of x was the way that it was defined was that it is a random set where every entry was sampled with probability xi, right? So the first thing that I can do is that use this definition in order to return a set. That is going to return a random set R. What is the problem with this random set? It might be outside the polytope. It might be a point that is not feasible. It's a good initialization, but it's not a feasible solution. So what contention resolution does, this particular scheme of rounding, is that it's going to basically take that solution, it's a very good initialization, and push it back in to a feasible solution. Basically, we are going to return a set S that is a subset of a random set R, where S is actually feasible. How we are going to do that? Well, it's by something that is called the C-balance contention resolution scheme. That's a definition. It's going to be a procedure that is randomized, but it is parameterized by any point x that selects a set S, which is a subset of a random set R, such that the probability that any single EI is in S is at least C times xi. Why this is good? Because if the function is modular, if it is linear, it is easy to show that the expected value of this set S is going to be at least C times the value of this point x. So that's very good. Suddenly we have an approximation guarantee. If we have something here, then C times that is going to give us an approximation guarantee. But when the function is not modular, this is not enough. We need another criteria. The contention resolution scheme should be monotone, meaning basically something like submodularity. If R1 is a subset of R2, then the probability that I'm going to see E1 in my set S should be greater than or equal to the probability that I see EI in my set S, given that Rx is R2. With these two properties, here is what we can show. Well, they can show is that the output of this monotone C balance scheme is going to be C times the solution that we get from the optimization. We can generalize, and usually this is what people do because they can get better results, by the B-C balance contention resolution scheme. It's practically the same thing. The only difference is that now we are going to look at a random set where elements are picked with a lower probability, B times X, and then it has exactly the same condition. Once we have a BC balance contention resolution scheme, these are all the results that we can get. If the function is linear or modular, a BC monotone contention resolution scheme is going to give us constant factor approximation that depends on C and B. The same thing for some modular functions, whether they're monotone or non-monotone. Do they exist? That's the whole point. They showed also that the existence of this basically family of contention resolution schemes. Okay, so for Metroid, for P-Metroids, for Knapsack, for intersection of Knapsack, etc. And here are the tightest results of submodular maximization under constraints that we are aware of, and they're all based on going to the continuous domain, solving the multilinear extension, using a rounding scheme. Contention resolution is not the only one. There are many other ones. It's one of the one of the schemes that has can actually handle a lot of constraints. And then for the Metroid, Greedy gave us 1/2 approximation T. Using this whole procedure, we can get 1 minus 1 over E approximation guarantee. For L knapsacks, we have L knapsacks constraints, not only one, but L is a constant. What is very interesting, we can still get 1 minus 1 over E minus epsilon approximation guarantee. If we have P metroids and L knapsacks, we can get approximation guarantees that only depends on P, independent of L, etc., etc. Okay, so what are some of the problems that we have not discussed? These are the research problems that people think about. So I'm going to talk about them in the last few minutes. We didn't talk about what happens if the data set changes, or what happens if we have noisy evaluations. So one of the problems with the continuous method is that they're slow. They give us the tightest approximation guarantees, but they're not the fastest algorithms that we can think of. Is it possible to speed them up? And then another question is that is it realistic to assume that we have an oracle value? So what are the some new frontiers that people think about in the era of big data? Well, these centralized algorithms are inherently sequential. You have to go multiple times over the data. They do not scale to huge amount of data, like hundreds of millions of data points. So you have to think about scalable methods. And one of the things that Jeff talked about is the streaming algorithms. Data points either come at a very fast pace, or you have a small memory. You can only go once over the data, and you want to have some solution. Another scalable solution is to distribute your data over many machines and try to parallelize the whole procedure. So in the streaming framework, this is the data, that is the machine you have. Pictorially, you cannot put all the data into your machine. Can you just read small parts of the data, and go once over the data and have some approximation guarantees? Okay, so I don't have much time. Basically, for the streaming framework, we want, on any streaming framework is going to be parameterized by 4 quantities, number of passes you have to make over the data, memory requirement, number of function evaluations, approximation guarantees, and then you can actually come up with some practical approaches that do not have any approximation guarantees. For instance, whenever a data point comes, if you see that increases the value of your current solution, you just swap with whatever you have. Okay? So you pick the first K, And once you have like k elements, a new data point comes, you just see whether it is possible to swap it with one of the things that you have, and it's going to increase the value, you do that. Okay, it works very well in practice, but then you can actually come up with examples that the approximation guarantee is horrible. And the reason is that this is too greedy, so people try to actually solve, to basically get around this problem. And the issue is that, you shouldn't be too greedy. You have to have some standards for which elements you pick, and basically you have to have a threshold. If the threshold is above something, if what you get is actually good enough, then you pick it, put it in your memory, otherwise you don't do it. And so basically the best approximation guarantee that we are aware of is 1/2, and it turns out that in order to get, it is impossible to get better than 1/2 approximation guarantee in the streaming model for monotone submodular functions under cardinality constraint, unless your memory increases linearly with the data. So if your memory is independent, let's say, some function of k, or sublinear with n, then you cannot get better than 1/2 approximation guarantees. Another, scalable solution is that, when you have, we can look at the distributed framework. So basically, the situation is that, okay, so the situation is that you have, a lot of data, but you have a lot of machines. You want to distribute the data over the machines. So what is the simplest way that you can do it? You just, put all the, put different parts of the data in different, on different machines, run, for instance, greedy-like algorithms on each machine, send the solution of each machine to a centralized machine, run another round of greedy on this machine, and then, pick the best element, the best solution among those. Okay? Does it work? Well, it turns out that, for arbitrary partition of the data, the approximation guarantee is not great, but then it turned out that if you randomly partition, then you get a constant factor approximation guarantee. Okay? So a natural question is that what is the trade-off between the number of rounds that you have to make and the approximation guarantee? So here it was a 2-round distributed algorithm. You can actually make more rounds and then get better approximation guarantees. Can you actually have algorithms that work with other type of constraints, non-monotone? Can you have decentralized framework that you have, a network of competing units, not only, this slave master framework? And so finally, let me just briefly mention that, submodularity comes in many, many different ways. One of interesting generalization of submodularity is over sequences. So far, we only have talked about selecting a subset that is feasible. Now you can think of a situation where you want to pick among policies, right? So in interactive settings where you pick an element, you see the realization of the element, and then based on the realization, you want to pick another element, et cetera, et cetera. Okay? And then, of course, if you don't have any structure, these problems are horribly intractable. If you have submodularity, meaning that the utility is going to basically, if you observe here, after few observations, the gain is going to be less than if you observe it earlier. Then you can get, you can basically show that the greedy algorithms or greedy-like algorithms are going to be provably good for policies. People looked at generalization of submodularity to any subset. You can say that how close my set function is to a submodular function, and then based on the distance that is usually one way, not usually one way is defined basically through this gamma weakly submodularity. How the greedy algorithm is going to work, and then. So here you can see that if gamma is equal to 1, then it is submodular, but gamma can be any number between 0 and 1, and then based on that number, you can actually get approximation guarantees. And it has a lot of interesting applications in regression, compressed sensing, even recently with neural network interpretation. And finally, we only talked about submodular functions over sets, but you can define submodular functions over continuous domains on any lattice, and this is one way to do it. So you have two vectors, x and y, in dimension n, and then f of x max y is going to be basically the pointwise maximum plus f of x mean y is going to be the pointwise minimum. And if that is less than or equal to f of x plus f of y, you have a continuous submodular function. This is an instance of such functions. And then under some conditions, you can actually solve these, these non-convex optimization problems approximately. And they happen to have actually a lot of applications for lifting discrete optimization problems, going to the continuous domain using these methods, solving them, rounding, and then getting very good approximation guarantees, even for discrete problems. Okay, so to wrap up, many decisions that we have to make are discrete. So one way to do actually optimization is that we just forget that they are discrete, and we just work in the continuous domain, even though the problem is discrete. But sometimes you can actually do a lot of interesting things in discrete domain. And submodularity is a fundamental notion, and it has a lot of applications. So Jeff talked today about information theory. He touched on economy of scale, and they happen to have a lot of applications in machine learning, game theory. And submodularity allows us to come up with strong approximation guarantees. So it's one way to, like convexity in continuous domain, not all problems are convex, but we try to convexify the problem in order to have approximation guarantees. The same way can be done for discrete optimization problems. We are trying to, very often we can actually find surrogate functions that are submodular and they approximate the true discrete optimization problem. And, we have shown 2 instances at least that submodularity is related to continuous domains. In minimization and maximization, actually the best algorithms that we know of in general are based on these relaxations. So that's the whole tutorial, and I hope that at least you learn why submodularity is a big deal to some extent these days in data science, and some of its roots actually were from information theory. And I hope that you get some intuition how and when you can use them, what are the algorithms. We have shown a lot of algorithms, but these are not the only ones. These are the simplest ones probably to explain. So thank you very much.